not only in terms of the quantity. I see many well-known faces, well-known speakers, and over the past decade I have heard in the executive committee meeting of the UISPP that one of the strongest, one of the best commission is the Archaeometry in the UISPP. I convinced that this current conference brilliantly supports and reinforces this kind of this. First of all, I must thank from the Archaeological Museum of Chania, especially Elena and her teams, to hosting us this wonderful venue. It might maybe not be appropriate to openly praise or serve the organizing committee, because I'm also a member of the organizing committee, but I must say without the dedicated work of Susan, Alessandra, and Phil, we wouldn't be here today. So thank you. And I would like to highlight my colleagues, Tamás Bubonyi, in particular regarding the website. Okay. And in terms of the program and the range of research topics, I believe that even the most detail-oriented scientists and researchers will find so their liking. There will be case studies, thematic and metallurgical presentations in aspects in inorganic historical materials, as well as some very interesting excursion. And at the end, I would like to thank again Eleni. It's a beautiful occasion that will take a very good scientific conference. I'm convinced that we will have 3 wonderful days, and I hope you will all enjoy all these days. Thank you again.
Just very quickly, a short announcement. There are some changes in the program, which I have to announce. The first 3 speakers are missing. So there have been problems with the visa. The first one is Indian, the second would be Daria Matinfra from Iran, and they didn't get a visa, of course, and also Hossam Hegazi couldn't come. So we are sorry not to have them here, but we have more time for discussion and for other things. So the other change in the program is the dinner. We have dinner in a different place. All of you, I think, have received an email with all details, the location, and yeah, whatever you want to know is there. So you are informed. There are more people coming tomorrow, and there are also several people, a rather large group of people who couldn't come but are giving the talks online. So we are not missing anything else from the program. It is, for example, our colleague from the Commission, Amin Emami, who is Iranian and also didn't receive a visa, of course, couldn't come, and other people, many other people from other places. So, yes, and somebody asked me to explain where the toilet is. So one is in the cafeteria and one is on the first floor downstairs. And I'm very happy to be here for the 10th anniversary of our Archaeometry Commission, and I would like to profusely thank Eleni, who is the director of this wonderful museum, very new museum. It is only 3 years old. 3.5, okay. We came here, Phil Betancourt, Professor Betancourt, Susan Ferenc, and me, 3 years ago, to visit the museum, and well, we were extremely impressed by the museum and by the facilities of the museum as well, and we discussed the possibility of having here a meeting of our commission. So here we are. Eleni, thank you very, very much for all of your support. I think we need an applause now. So, and now I give the word to our chairman of today, Michael Krüger and Kostis Kostistakis.
Dear friends and colleagues, good morning to everybody. And I think before to start such a very interesting session about ceramics, allow me to thank on behalf of everybody the organizers of such interesting meeting and those who for many years worked for the creation of such amazing and modern, in many ways, archaeological museum.
I would like to invite the first speaker, Christian Skark, who, together with Tobias Kowronek and Constance von Rüden, they are going to talk about talc as white pigment on polychrome Camara's ware.
Thank you very much, dear ladies and gentlemen. Thank you for inviting that contribution for an oral presentation. I appreciate that also on behalf of my co-workers, Dr. Tobias Kowronek and Professor Constanze von Rüden. One of my questions is whether talc was the raw material on white decoration in Middle Minoan Camara's ware, and can one see the conversion of talc to ansatite during firing? Can one, what sources of talc may be appropriate for this white paint? The investigation of some shirts and talc samples should yield some answers. The Camara's ware was produced between 1900 and 1700 before Common Era. It was typical for the Proto-Palatial period. Camara's ware is a polychrome decorated pottery which presumably was used for conspicuous consumption in court-centered buildings, the palaces, and as well as in other houses. It was not an everyday item. The polychrome decoration consists of a black layer with white and red or orange, mostly geometric ornaments. These two shirts, which presumably were found in Knossos, are now located in the Heidelberg University Museum. They were not published. The right-hand sample shows white painted clay dot protrusions, and there are two circles of them. They are separated by a white band, and under the lower dot circle there's an orange band. The left-hand sample B is displays a leaf. Also, nein, das war falsch. Zurück. Displays a leaf-like white paint. The barbotine like decoration of the sample A hints to a production in Middle Minoan 1b or early Middle Minoan 2, whereas the sample B was produced later. At both sherds, the white paint was scratched off with a surgical scalpel. In the subsequent investigation, we want to find out what mineral origin the white paint has. It may stem from talc. This phyllosilicate may be applied before firing and will be transformed to anstatite during firing above firing temperatures of 950 degrees Celsius. Alternatively, the white paint may consist of lime silicate white. The differentiation between the two white paints, talc white and lime silicate white, will be based on the ratio of magnesium to calcium. The further investigation of the scratched white paint were undertaken by X-ray diffractometry and by scanning electron microscopy combined with X-ray spectroscopy. On the base of the destructive sampling, one can avoid the detection of calcium-bearing minerals at the surface of the sherds. The essential composition of the white paint can be seen. Talc or steatite samples were investigated by X-ray fluorescence. The X-ray reflexes of the diffractometry point to anstatite, and this shows this diffractogram of sample A, and the same exhibits the diffractogram of sample B. The preparation of the scattered particles of the scanning for the scanning electron microscopy is shown here. It displays sample B, and I want to go to further detail to this particle at 7 o'clock. Here you see this particle in the scanning electron microscope picture. It's a two-layered particle. On the sheet of white paint, you see at the right hand, and it's sintered to a layer of black paint, which is more vitrified on the left. By the X-ray spectroscopy, one can identify several spots, or one can investigate several spots, and the results can be interpreted as anstatite. These crystals have an elongate habitus and can be seen as pseudomorph to platy talc crystals. As a consequence of firing, they show a sintered and almost vitrified texture. In both samples, one can identify anstatite in 47 measured points. The molar ratio of calcium to magnesium is shown here. Calcium lies below 5 mole%, and the magnesium lies between 10 and 25 mole%. Thus, all points display magnesium to calcium ratio above 1, suggesting a talc origin of the white decoration. In none of the measured points could be identified a lime silicate white with a high calcium rate. So we try to compare this to other investigation, and in other investigation of Middle Minoan pottery, the white decoration was also found due to talc white. On the other hand, in many samples, the white decoration was found as a lime silicate white. For some of these investigations in the literature, there are also quantitative data available from Commos and Festus in the south, from Knossos in the north, and Palakastro and Mochlos in the east. So if one looks to the magnesium to calcium diagram another time, you see the samples from the south are plotting in the field of magnesium to calcium above 1, whereas only single investigations in Knossos and Palakastro offer these kind of magnesium to calcium ratio. Most of the Knossian samples and the other samples of the East display a ratio below 1, magnesium to calcium ratio below 1, suggesting a lime silicate white paint. But the higher calcium rates may be influenced by a superficial contamination with carbonates, and this may be erroneously identified as a white paint when non-invasive investigations methods like particle-induced X-ray emission are used. So the occurrence of the talc white on Camara's ware may be one of the innovations in the pottery making during the Proto-Palatial period, apart from polychrome decoration and the successive itself and the successive introduction of the potter's wheel. All this happened on the background of a centuries-lasting continuity of pottery production in the Messara plain concerning clay recipes, firing techniques, and vessel setting. Obviously, this knowledge was transferred for several generations. So, what sources of talc will be used for that talc white? It might be the residues of steatite which were sampled during stone vessel and seal carving. But for stone vessels and steel, serpentinite is prevailing. Thus, a dominance of chrysotile is more probable instead of talc and steatite. On the other hand, talc and steatite may occur in various positions in Cretan geology. The occurrence may be linked to ophiolites in the uppermost unit and to the in the Plattenkalk, in the lowermost unit of the Cretan knapsack. So we could investigate several samples from Kataro and Sarakina and from the region of Lenders. And in this geological sketch map, one can see these sampling sites, the outcrops of the uppermost unit or the Plattenkalk. So the analysis with X-ray diffractometry results in high magnesium rates in the talc samples, and they plot in the field of sample B and statite in that magnesium to calcium diagram. Regional origin of the talc for the white paint is probable and not excluded, but it's not yet fully proved. To come to conclusions, the investigation of the two shirts reveals high magnesium contents. The magnesium is bound to anstatite, which hint to talc as origin of the white color and indicates a firing temperature above 950 degrees Celsius. High magnesium contents are also common in other shirts from the Messara plain. The most likely source of talc for white ceramic paint lay in Crete, but it's not fully proved. So I'll thank you very much for the attention.
Thank you very much for this very interesting paper. We decided that because we have plenty of time to postpone the discussion after the second. No? All right. So we have some minutes for questions. Any questions?
It's just a simple question. Thank you very much for your talk. I was wondering, what would be the benefits of using talc versus lime in reality? Just from a layman's point of view.
I think it's a more bright white on one hand. On the other hand, you are right, the problem is the adhesion of the talc white on the pottery will be hindered because also talc is not very easy to work with, as talc has hydrophobic characters, and that's not very easy to prepare a slip, a watery slip with that for painting a white ornament. But obviously it was used. It was used for a certain time span. It wasn't used for a huge time period.
Thank you very much. Yes.
More questions, please.
Yes, I'm wondering about the research you have been doing. Can you tell the origin of these materials as well? You have been studying these different deposits.
So we are not really convinced about the Cretan origin of the talc. That depends also on you may prove it with a principal component analysis or something like that. But if we put together all the results, we don't have enough examination points to prove it really on a hard basis. So, okay, principal component analysis will give you some answers, some results, but you have to take care of the basis of the liability of these results you have. You can every time you can see something in a principal component analysis. So we have to put together more information about the talc sources, particularly from Crete.
Yes, you need a lot of data, yes. Several thousands, I suppose, with principal components.
No, not several thousand, but now we are at the base of the liability with 50 samples, and we need some more.
Definitely, yes.
Yeah. It will be representative if we have some 20 samples more, or something like that.
And that would be enough for principal components?
Yeah.
Yeah.
It should be above 50 samples in your data set. And you have to control it. There are several statistical parameters to control this. And then it will be sufficient or not sufficient. Until now, it's not sufficient.
Thank you very much, yes.
Okay, many thanks. And now let's move in another interesting topic and different topic, the archaeology of linear bit tablets by Ina Berg.
All right, thank you so much for letting me come and speak to you today. I should preface my talk with two apologies. One is that my topic is not just archaeometry, so I will have a multi-method approach, and so you will see some X-rays and you will see some experimental archaeology also. And the second apology is that so this is a very new project for me, and I'm only able to present really very preliminary results on some of the information, and that was set back further because I had a bereavement in my immediate family just recently. So unfortunately, I haven't been able to complete the data collection yet for all of the work that I wanted to do. So it's just a taster really today to give you an idea of what the potential is. All right, I wasn't quite sure who was going to be here in at this conference, so you forgive me for those of you who are well aware of all the administrative object details. For those who are not, just a brief summary of the different kinds of clay administrative objects that are around, and some of which I have been able to analyze and look at. today's purpose, I'm focusing on the linear B tablets, but I've also started looking already at roundels and some nodules. So just to sort of, I guess, to preface that these different kind of administrative objects that you can see here, from tablets to roundels to noduli, nodules and ceilings, that they have potential differences in their geochemical profile, as into where they are coming from. Are they locally produced and consumed, so to speak, or have they traveled with an object? And so part of what I'm looking at is trying to understand that. In the past, as you're well aware, especially in terms of the tablets, a focus has been really on the text, on the seal imagery, and to a slightly lesser extent on a scribal hand's archival organization and shaping techniques. But really, for my purposes, I'm looking at them as archaeological objects exclusively. And then on the right-hand side, you can just see some images at the top of linear B tablets, and then below different kinds of additional clay administrative objects. And so in terms of my research objectives for this project is to really treat administrative clay objects in their own right as archaeology, rather than as a carrier for a text. So for all intents and purposes, I pretty much ignore the text. And I'm particularly interested in understanding the entire chaîne opératoire. So I'm looking at, raw material, their composition, the processing potentially of the clay, the shaping techniques, the inscriptions, reuse, and then deposition. And really, I'm interested in both things. Obviously, is the objects themselves, but also how then my sort of revelations, hopefully, can help us understand their function of these different objects a bit better. And the methods I'm using is experimental archaeology, X-radiography, and PXRF. And as I said, for today, I'm just really talking about very preliminary starting project today. So I'll start off with the PXRF and the making of clay tablets. And as you can see, I've been able to get access to 39 linear B tablets so far that are available in the Ashmolean Museum and the British Museum, and that's the total sum of linear B tablets that we have in the UK, as far as I'm aware. What brings them together is that they all have a stated provenance as coming from Knossos. So one question for me was, would they all fall together in the compositional matrix? And obviously, in terms of the assumption that we have, is that linear B tablets were manufactured locally and used locally in terms of the clay. So the clay should have a local Knossian signature. In terms of the analysis, we have a Niton XL3 analyzer in my department, and then I use that in order to do a principal components analysis, and you can see the results on the screen showing the three components. So the font has changed a little bit, which has also changed the orientation of the text and the overlap that wasn't there before. But hopefully you can still see enough. So I guess what you can see initially is that both the Ashmolean and the British Museum tablets, they all fall into the same sort of cluster. So assuming that they are from Knossos, they seem to be both in both locations, they seem to be from Knossos. And the other, I guess, piece of information is that there are, at the moment, no obvious compositional groupings to see. So the assumption there is, therefore, that, in fact, they are all coming from the same location. In the process that I'm in at the moment is that I'm looking at additional material to supplement this, to give us a little bit of perspective. So at the moment, I am analyzing Knossian pottery at the Ashmolean, also Knossian ceilings, and also some non-Cnossian material just for diversity. And really what I'm interested in once I've finished this process is to look at potential clay preparation and clay choices that have been made in the composition. Then moving on to X-radiography. So I started a process of experimental replications of different kinds of tablets. So this is based on Anna Jetson's lovely work, and if you're interested, and you might want to use that for students as well, there's a lovely video of how to make a linear B tablet, so that is quite good fun. And so basically she distinguishes between simple clay tablets and folded clay tablets, and so I've got some clay, and I did my own folding and shaping of the tablets, and I think it's very easy to see. They look very, very different in terms of their X-ray result. So on the left-hand side, here you've got the simple tablets, and on the right-hand side you've got folded tablets. So simple ones are really very straightforward and very simple. You just, have a coil or a lump of clay, and you just squish it down. And the folded tablets, you kind of roll them out. I used a rolling pin, or you can just flatten them with your hand, and then when you are folding a piece of paper in order to stuff it into an envelope, you kind of fold the tablet. And so what you can see is when you have a top-down view and the simple tablet, it is simple, straightforward, not much to see, no patterns. And the same is here on the cross-section, where you can see a linear orientation, in this case horizontal, of any voids. In the folded clay tablet, you can see the folds really very clearly in the X-ray, in a top-down view. And then in the cross-section, because there is air gaps between the different folds, you can actually see the different folds as well, really very clearly in those two different techniques. So then I took it a step further, and I tried to see if it would show very clearly the different ways in which tools might have been used or hands might have been used. So I just used the rolling pin in different directions, and you can see it straight without too much interpretation from me. So here you have a rolling pin, and I rolled it from the center horizontally left and horizontally left and right. Or here I started in the center and then up and down. And then here I just used my palms in order to squish down the tablet, and that all gives you very clear indicators of each of the methods. The next thing, again, sorry about the switch in spacing of the text. We then X-rayed the actual tablets, in this case in the Ashmolean Museum. The ones in the British Museum, I'm still hunting them down for the X-ray action that is still to come. So here at the top we have a tablet from the Ashmolean Museum, and here it's inverted, so what was previously black is now white. So black indicates the more solid part, and then white the more where there is less material there. And so what you can see really very nicely, that in this tablet you have what has been interpreted as a string that has been laid lengthwise, and you can see not straight but sort of curved. And that matches what we see also in some remains that are sort of broken. And so here you can see an example also from Knossos, published by Fluda and Notti. And so you can see here the string still there. And what is interesting amongst the Ashmolean, I'm only showing you one example, I've got somewhere between 5 and 10. So this sort of addition of the string was actually much more common, I think, than we previously thought. What else have we got? So I tried to see what we can do with inscriptions. So again, I tried my hand. This time I didn't try to imitate linear B, so I just used a regular alphabet. So a replica table at the tablet at the top inscribed with letters, and then I would then obliterate them using just either, just some slip or just, again, sort of squishing it down and obliterating it. And then what I did is I tried to use different stages in the manufacturing process, so to obliterate the original text. So at the top, I tried it while the tablet was wet, and as you can see, when it's done while the tablet is wet, it completely obliterates the text that was inscribed at the time. However, if the scribe had waited until the tablet was leather hard and then tried to erase the text, it wouldn't be that successful. And so here, this is completely erased. When you look at it visually, it's completely erased to the visual eye. But when you look at it on an X-ray, you can actually see the text still visible underneath that surface. So it gave me hope to see whether perhaps we can look at an X-ray, just some linear B tablets, to see if we can find hidden text that otherwise isn't visible anymore. And I'm afraid we're still at the very beginning of this. So I've got a colleague, Dr. Victoria Brandon. So her task at the moment is to help me do this. So what we've done is we've X-rayed the tablets in the Ashmolean, and we're overlaying it with the text in order to spot and see if there are any examples of bits and pieces, hazy lines that might indicate text that previously has gone unnoticed. So that's, again, at the very beginning. There is much more work to be done, as you can see, and at the moment I'm only working with UK material, so I'd like to kind of expand. So obviously I want to do more PXRF of Cnossian pottery, the ceilings, but also other administrative objects, because I think that comparison between linear tablets and other kinds of administrative objects would be a really interesting way to think about the uses and the functions of these objects. And also I want to expand into non-Cnossian materials, as in clays. The X-radiography of the British Museum is still to come, and then because of the string that we see in the tablets, I'd like to then do a few more sort of replica studies looking at different kinds of organic fibers, perhaps that can be seen. And I've done some work on roundels already, where, for example, I can distinguish different string, not the materials, but I can see different knot patterns and different ways of turning the string. I didn't bring it to show you today, but that's been done already. So, yeah, so this is just work in progress, but I hope it gives you an idea of the potential of what there might still be to be found in the linear B tablets. Thank you.
Many thanks for the presentation of such a promising project. Any question for Ian? For Ina? Sorry.
Thank you very much for the talk, were very interesting. I have a technical question regarding the X-ray imaging. Did you use a tomography? So what you showed before is a tomography slice or a radiography?
No, it's just pure radiography.
Is there a reason for what you didn't try tomography? Or?
I did use it not on the tablet,
I mean on the inscription, to recognize the inscription.
No, I haven't done that. It is possible. It's just my experiments with CT have been really frustrating, to be honest.
Okay.
It is really time-consuming, and then especially the post-processing. I mean, the work that you have to do afterwards with the software was just so difficult when I did it with pottery that I haven't even dared think about it. But you're quite right. There is a potential but I would need to...
No, especially considering that the objects are from the Ashmolean Museum and British Museum, because, you know, Manchester has a CT scanner on the Harwell site in
Yeah.
Oxfordshire, which is a very powerful machine where we scan large objects, so I'm sure you could get a very good result. And if you want support for data analysis, I'm happy
Fantastic.
to point you to the people that can help you.
I mean, the good news is actually the British Museum has just purchased
Oh, I know,
a CT scanner, and so they have been doing their wonderful project with the cuneiform tablets, and that kind of what got me thinking also.
Because this is what I was thinking, because it would be definitely a very good step forward for
Exactly.
Thank
so,
you, thanks.
But so I'm begging at the moment to see if I can get some CT time with them, but at the moment we're just talking about regular radiography.
Okay, thank you, thank you very much.
Any other question?
Thank you very much for beautiful talk. Just out of curiosity, what was the purpose of using the cord?
Good question. We have some examples also in Pylos, and it seems that the cord might have been used to link different tablets together so that you don't just have one, but you have multiples. But I've got my own little ideas perhaps about what it could be used for, but I just need to think about it a little bit more. But yeah, for me, it's not quite sure yet. But Anna Judson says that she thinks maybe if they were transported, that by having a cord in there, if they break, they will not fall off and you're missing part of the tablet. It kind of acts as a glue to kind of hold them together. That is a possibility. I think I'm not quite sure whether that really works for me as an interpretation, but so there are different ideas around, but I'm not quite sure yet that we've really captured what the purpose was of that cord. Thank you.
Generally speaking, how many tablets we have with the string?
Well, I mean, I would say, I've got 35 in the Ashmolean that we X-rayed, and of those, somewhere between 7 and 10 have a string.
7 and 10. So
it is a quarter or a third, I would say,
yes.
potentially, that have a string. So it is much, much more common, I think, than we previously thought.
I see.
Yeah.
And the string goes along the tablet, on the long side.
Yeah. But again, puzzlingly, not straight. As, you know, I would do it, being German, straight. But, it's kind of bent. So again, I'm not quite sure what that signifies. So, and that is pretty consistent as well. So you see it as like a curved one, as you saw here.
All of them are curved?
Yeah, pretty much, yeah.
The other question is, did you manage to see differences comparing the results of the XRF?
I haven't got that far yet to look at if there were differences between those that have string and that don't have. The other thing that I want to do also is a lot of the tablets are, some are, leaf tablets, other are larger tablets, if there is a difference in what clay was used. So there's quite a few things. And then the other thing that I need to
That's what I meant, actually.
Yeah, and then the other thing I need to look at a little bit more, because obviously a lot of the tablets are very highly burned. So I need to see also if that, changes the composition somewhat.
Of course.
Any other question, please?
Very much. Another question that I have, what could be a reason of using a folding technique? What do you think?
I have no idea. I mean, having done it, it is a very laborious way of, and it looks really unsightly afterwards, because if you may remember, so it just looks odd, on the cross section. I'm not, again, lots to think about. The ones that I've seen in the Ashmolean, they look entirely different. They're not made, I've not seen a single one that was made in this folding technique. All of the ones in the Ashmolean are not, and they're not like this one either. They are really very chunky. They almost look, I was trying to explain it. Do you remember when, like my grandparents, when you write with ink, and then you had a blotting device that was kind of sort of almost crescent shaped? So that's kind of obviously the look of these tablets. So they're not made in, as far as I can tell, in either of these two techniques that Judson has proposed. So again, there is a bit more replica work for me to do to think about the creation of this.
Any other question?
Yes, thank you. I was just wondering, these tablets are for administration purpose, and you said that the cord was curved. It's just an hypothesis. I don't know anything about this, but they may have been just suspended around some storage jar. Could it be possible?
I think all of it is on the table as potentials, because we just don't know that much really about the organization in baskets and so on. So so it's all something to consider, I would say.
Okay, thank you.
Any other question on linear B tablets? It is a very interesting topic, really, and enigmatic in many ways. Okay.
Thank you. Does PXRF really work for provenancing clays? I don't know much about the topic. I was just thinking that maybe laser ablation would be good to get a really wide assortment of elements and then use principal component analysis. So have you tried, or has there been laser ablation done on clays from Crete?
Not sure. I'm sort of a relatively newcomer to this particular area. There might be people here who know the answer to that question. In terms of PXRF for clays, I know there was always, going back 10 years, there was a big debate about, whether it should be used on clays at all. I think, and that's why I guess it started out with being used on obsidian in particular, which is very consistent. But I think I'm following Patrick Quinn's kind of approach in that if you do it carefully and thoroughly, there is information to be had, and I guess it depends also what you're trying to do. So I'm not trying to link it to a specific provenance. I'm not looking for deposits in Crete in order then to match it. What I'm looking at is internal consistency to see whether the tablets all were from the same composition or different compositions, without necessarily then trying to link it specifically to an origin as such. And then the same with the other clay administrative objects. Again, I'm not interested to find out where they're from at this, certainly not at this stage, but just to see whether they are very variable in their composition or very homogeneous. So hopefully the answer is yes. I think it is workable, but I'd like to get more samples for sure.
Yeah, I'm sure there are people here who know about clay provenancing. The question for me was more that, is it important to know the ratios of different elements or the absolute numbers of the different elements, and how many elements could provide useful information? But I'm sure we'll hear about it.
Dr. Vlasaki wants to speak.
I don't say anything about the provenance because a lot of analysis must be taken for Cretan, tablets. But I was wondering about the tablets with the cord. inside. And it depends. Maybe somebody must work on to see what the content of the text. If they have the same use as the clay labels in the outside baskets or boxes or like that. Mrs. Fluda, Dr. Fluda, who has, you said, has worked on that, has any result on this? Do you, or you?
I'm seeing her tomorrow. I'm sorry, I'm skipping out
here.
of the session for tomorrow just to see Dr. Fluda, and then hopefully I might be able to bring back some further information.
Okay, thank you.
Any other question? Yes.
Thank you. Just a small observation also regarding the previous question. There is a very interesting work similar to yours, on cuneiform tablets, on geochemical research performed by Yuval Goren, Hans Mommsen, and Jörg Klinger, and it was published in 2011, I believe, in Journal of Archaeological Science. They used advanced statistics, but the research was made by PXRF. Yeah. And the results are really outstanding. And so I think that using PXRF to burn clay is a very promising method. Also to mention that they used potassium-titanium test as a to first classify the cuneiform tablets, and maybe it will be also useful for your research, because in their example show that it brings very interesting results.
Thank you. Yeah, it's lovely research they have done on the tablets. Yeah.
Okay, then let's now to move in a coffee break, which I think all we needed.
I just wanted to say we have plenty of time, as you have noticed, so I would invite you to have a look at the museum as well. In your bag you have a catalogue of the museum, so it is going to be useful, I think, during your visit. And presently also the coffee break will be ready. So we begin again at 11:20. We keep the schedule.
Mr. Minos, can you hear me? Okay, give me a second to raise your voice because I can hear you very well. Can you please speak again? Again, please. Yes, perfect. Please try to speak, say a few sentences to check if you hear yourself.
Good morning. I would like to begin by thanking the organizers for allowing me to present my research at this conference. I don't hear myself.
Okay, perfect. Because it's a bit tricky, because you are taking the sound from the sound console. It's a bit tricky to isolate your microphone so you don't hear it again. Okay, do you want to try to put your presentation online?
Yes, please. Yeah.
Okay, please share your screen or your camera.
Seconds. I'm in presenter view, so I'm going to share just the window.
Yes, sir.
Can you see my presentation?
Yes, perfect. Let me check how I'm going to present it to the amphitheater. Okay, it's perfect. It's full screen on the projector, so you can present directly. Are you going to? Yes, of course, I can see the PowerPoint change. Are you going to open the camera?
Unfortunately, my camera's not working today. Sorry.
Okay, no problems. Okay, I suppose that you can see our camera. It's from the amphitheater. So you can check the reactions or whatever you want, and also at the end of your presentation you will take questions from the audience if they need something. I will give them the microphone so you can hear the question well.
Great. And it's 15 minutes, right?
Correct.
Perfect. Great.
Okay, you can stay inside. I will mute the laptop.
Okay, thank you so much.
You're welcome. Yes, please.
Never mind. I think I got it. There was an issue with sharing the correct window. It just disappeared, but it seems to be working now. So never mind.
Yes, I can see your presentation.
Perfect.
Hello, Mr. Proven, can you hear me?
Hello.
Hello, can you hear me?
Yeah, I can hear you.
Okay, let me check a moment your voice levels on the auditorium. Okay, I think it's very nice. Do you want to start presenting your PowerPoint so we can check if it seems well?
Is it visible?
Yes.
Right, I will make it slideshow.
Yes.
Yeah.
Okay, perfect.
Is it okay?
Yes, yes, I can see it very well.
Yeah, thank you very much.
Okay, so you will present directly from your teams. You will be here on the auditorium and on the live stream. You won't hear yourself, don't worry.
Yeah, sure, thank you.
Okay, and after the end of your presentation, you will maybe you can take answers, questions from the audience. So I will give them the microphone so you can hear the questions.
Yeah, sure.
Okay, thank you very much.
So the recreation is over and holidays are over. From now on, we are keeping a very strict schedule. I give the word to the chair ladies of this session, Nota Timopoulou and Eleni. No, Daro, yes, I know, but why are you there?
Who is also the first speaker in this session. First paper is by Eleni Nodaru and Dr. Metaxia Tsipopoulou on pots and goats in East Crete at the end of the Bronze Age, a petrographic study of ceramic materials from the late Minoan 3C shrine at Halasmenos. Eleni Nodaru.
Thank you so much. I would like to take 1 minute. Metaxia Tsipopoulou and I would like to thank the organizers for having us here for this amazing venue and the whole organization of this conference. So, over 3 decades of survey and excavation in the Isthmus of Hierapetra have brought to light important settlements of the late Minoan 3C period and demonstrated common trends in the settlement planning, the architecture, and the material culture. Καβούσι Βροντάς, Κεφάλα Βασιλικής and Halasmenos, all at a distance of almost or less than 5 kilometers from each other, have created a rather complex picture with megara, shrines, goddesses with upraised arms, and other types of cult equipment, along with significant pottery assemblages, to mention just the clay objects. The aim of this presentation is to investigate the recipes of manufacture of the cult material from Halasmenos, compare with the rest of the pottery, and address broader issues of pottery production and distribution in the Isthmus of Hierapetra, integrating Halasmenos in the ceramic scape of the area at the very end of the Bronze Age. The settlement of Halasmenos lies on a steep hill at 240 meters above sea level to the south of the Ha Gorge, close to the modern village of Monastiraki on the northern Hierapetra Isthmus in East Crete. Excavation began in 1992 as a Greek-American collaboration led by Metaxia Tsipopoulou and the late William Coulson. It represents a single, short phase of occupation, a more or less closed LM3C deposit. Strategically located near major land and sea routes, the site controlled access to both the fertile plain and trade axis running east-west and north-south across the isthmus. Its well-preserved architecture follows the detailed study, its well-preserved architecture allows the detailed study of construction methods, spatial organization, and room functions. The settlement covers about 4,000 square meters and consists of 3 sectors. Sector A contains 3 megara, suggesting organized communal activities. Sector B comprises smaller domestic units used mainly for food preparation and storage. And Sector 3 contains a public shrine, a major cult building of the settlement. The shrine, which constitutes today's topic, is a megaroid structure overlooking the Gulf of Mirabello. It has 2 rooms, 5 benches, a possible hearth, and a north-facing entrance to the sea. In this presentation, we focus on the cult equipment, particularly the large female figures, the so-called goddesses with upraised arms. The figures, made from different types of clay, have varying designs with elliptical skirts and long stylized hair, occasionally with traces of black paint. The shrine also contained these cylindrical vessels with plastic snakes, the so-called snake tubes, and these panels called plaques. The latter were found along the long bench in the first room, suggesting that they initially were hanging on the long west wall. Other items include simple calathoi, these bowl-like vessels, and fenestrated stands. In terms of pottery, 3 large pithoi suggest that the shrine had a community-level storage capacity, possibly linked to rituals or feasts. Other vases include tripod cooking pots, basins, cups, and bowls, the usual domestic vessels. In terms of, now let's move to the analysis. The petrographic analysis included representative samples from the ritual objects and the pottery, offering thus the opportunity to study the assemblage in an integrated manner. The analysis of the cult equipment identified 3 main and very distinctive fabrics representing different geological environments. The first is the granodiorite fabric. It is buff firing, coarse to semi-coarse. It is well known in our area and has been described at many instances. It is characterized by large angular fragments of diorite, and it's very homogeneous. 1/3 of the goddess figures and almost half of the snake tubes and plaques are manufactured in this fabric, but it's very common also in cooking pots and a few basins. The most common fabric in the assemblage is the ophiolite-related, also coarse to semi-coarse, also buff firing, with a very fine matrix. The non-plastic inclusions are rounded and evenly distributed in the base clay, leaving no doubt that they were added as temper in the clay mix. There are 2 variants. The dominant variant contains metamorphic rocks and comprises the 2/3 of the goddess figures and slightly over than half of the snake tubes and plaques. The majority of the closed and transport and storage vessels is also manufactured in this fabric. Then there is a second variant, the one on the right, that contains volcanic rocks. This recipe is also connected with the same geological environment, but the raw material derives from a different source. We have only one goddess fabric, only one goddess fragment in this fabric. The third fabric, unlike the other 2, is red firing, non-calcareous, and is characterized by metamorphic inclusions. In this fabric, there is no cult equipment whatsoever, only calathoi and all kinds of domestic vessels. So now let's see how all this relates to the geology of the area. The metamorphic fabric is connected with the phyllite quartzite series outcropping in the broad area of Kavusi in the Thripti mountain. The presence of a late Minoan 3C kiln at Kavusi Vronda might be connected with the production of the red metamorphic fabric here at Kavusi. The granodiorite fabric is connected with the relevant outcrops in the central and western part of the Gulf of Mirabello, in the broader area of Gourgnac Lochorio. Although the settlement of Gourgnac was abandoned earlier in the late Minoan 3B period, there are other important settlements like Vrocastro, and pottery production must be connected with their presence in the area. Things are more complicated for the ophiolite-related fabrics. They are connected with what we would traditionally call a south coast fabric, and we would associate it with the broader area of Myrtos, which is further west of the yellow line, of the yellow arrow. However, there is a small outcrop of flesh at the base of the hill of Halasmenos, right on the eastern part of the Ierapetra Isthmus, the black arrow. The presence of a particularly impressive LM3C kiln at Halasmenos must be connected with the production of pottery in this fabric, at least the main variant containing metamorphic rocks. The volcanic variant could be a product of the south coast. Now, let's see how we can interpret all this. There are two recurrent questions in the study of the late Minoan 3C cult assemblages in the bibliography. The first, is there specialized production for the cult artifacts? And the second, can we distinguish sets of cult artifacts? The petrographic evidence from Halasmenos answers clearly to both these questions. At Halasmenos, there is no special recipes. The granodiorite and ophiolite fabrics are exactly the same for cult material and domestic pottery. We can also suggest that there do exist sets of vessels, since in this fabric we have goddesses, snake tubes, and plaques. If they were brought as sets to the shrine, that's a different story, and we will never know. For the kalathoi, the situation is different. In their vast majority, they are encountered only in the red metamorphic fabric, which is used only for domestic pottery, confirming what we suspected, that kalathoi form part of the regular domestic assemblage and they get ritualized when used in a ritual context. In order to put Halasmenos into the context of the LM3C period in a more general way, we need to examine the cult material in conjunction with the contemporary assemblages from the other sides of the Isthmus of Hierapetra, namely Kefala Vasilikis and Kavousi Vrondas. All three assemblages are currently under study for publication, and consequently, we do not have complete data for any of them. Therefore, what I'm presenting today is based on preliminary publications and/or personal observation, as well as discussions with the people studying the material. So let's see the representation of the main fabrics in all three assemblages. There is no cult equipment in the red metamorphic fabric whatsoever. In all three sides, the kalathoi are manufactured almost exclusively in this fabric, but as we said, kalathoi form part of the regular domestic assemblage. The closest source for the production is Kavousi, where we also have a kiln. It is interesting that among all the cult objects from all three sides, there is a single goddess in this fabric, and it was found, of course, at Kavousi. The granodiorite fabric is present in all three sides, but at different quantities. At Halasmenos, 1/3 of the goddesses and almost 50% of the snake tubes and plaques are in this fabric. At Kefala Vasilikis, where the amount of cult material is quite restricted, 2 out of the 3 goddesses analyzed are also in the granodiorite fabric. At Kavousi, on the other hand, where we have over 30 goddesses, 30 snake tubes, and 30 plaques, only 2. There are 2 goddesses, 2 snake tubes, and 2 plaques in the granodiorite fabric. Its presence is minimal. And again, because we have 2, 2, 2, it's very tempting to talk about sets of objects. Last but not least, the ophiolite fabric constitutes the most frequent component in all 3 sides. Over 60% of the cult material of Halasmenos and Kefala, and 80% of the cult material from Kavousi is manufactured in this fabric. The pottery kiln found at Halasmenos and the fact that the site lies on top and next to ophiolite outcrops makes it reasonable to suggest that most, if not all, of the ophiolite pottery was produced in workshops located in the vicinity of Halasmenos and distributed to the neighboring sites, even Kavousi, that has its own kiln but apparently produces a different type of pottery. To conclude, the aim of today's presentation was not just to show the fabrics of the cult material from the shrine of Halasmenos. We used the analytical data in order to demonstrate the degree of interaction among the sites of the Isthmus of the Ierapetra and the interconnection between producers and consumers. It appears that at the very end of the Bronze Age, the Isthmus of the Ierapetra constitutes a dynamic landscape with a diverse network for the procurement of typologically shared sets of material culture. Thank you.
Thank you, Eleni, also for keeping in time. And we have 3 minutes for questions. Please. Anyone? Any questions? Dr. Jumlia? Yeah?
Thank you very much. Very small question, probably I just missed it. What kind of organic tempering they used? You mentioned the organic tempering.
Sorry.
Okay, we can tell from the voids that was something organic that burned out, but I cannot really tell if it was chaff or something else. There are new studies that say that they used to use weeds, seaweeds, dried seaweeds, but from petrography, I really cannot tell. I just see the elongate voids, and I know it's something added, but I cannot tell what. Yeah.
Thank you, that was really interesting. Just a quick question. In your opinion, the different specialization between different kilns on domestic versus ritual vessels could be linked to different properties of the specific ceramic fabrics, like more refractory or something like that, or just local traditions?
No, these clays, they definitely have different properties. The buff-firing clays, which are more calcareous, they're more plastic, so it's easier to shape what you want to make, and they hold the decoration better. Unlike the red ones, which are less plastic, they work better for cooking wares. That's why, I mean, in terms of goddesses, as I said, we only have one, and we really, I mean, the Jerry Giselle, who's studying them, she's really puzzled about the fact that there's only one in the whole area. For making figures, it's much better to use calcareous clays. So that's why the ophiolites work better. Yeah.
Okay, thank you very much.
So we have to proceed to the next paper, which we will attend by Zoom connection. It's by Chase Minos, Technologies and Tradition or Innovation, a technological and compositional study of late Bronze Age utilitarian pottery from Enkomi, Cyprus. Please, Lefteris.
Can I speak now? Good morning, everyone. I would like to begin by thanking the organizers for allowing me to present my research at this conference. Unfortunately, I'm not able to attend in person, despite being just east of you all on Cyprus. But again, I want to thank them for allowing me to present remotely regardless. Today, I'm going to be talking about part of my PhD, which investigated the raw materials used by fast potters at 2 different sites during the early centuries of the late Bronze Age on Cyprus, where a new technology, the potter's wheel,
None of these subgroups could be further distinguished by wear, chronological periods, or manufacturing techniques. At least a few examples of each wear and different manufacturing techniques are represented throughout the late Cypriot 1 to 2B periods in all subgroups. This seems to strongly support the idea that both raw materials and recipes seem to have been shared by multiple producers. And this was then supported by the handheld XRF results, which, as I said earlier, were intended as a pre-screening tool to identify any potential geochemical groups. Instead, it ended up supporting the petrographic results. Despite numerous statistical analysis, mainly PCA, clustering, and discriminant functions, as well as biplots of various elements and element ratios, there were no clear patterns that emerged in terms of wear, manufacturing chronology, or petrographic group. And this is illustrated here by the large cloud of chemical compositional data from the PCA, in which chromium, nickel, and magnesium oxide carried the most weight, but not enough to really determine any discrete chemical groups. Of course, I understand that the handheld XRF is not the most precise method, and so it was decided that several samples would also be submitted to ICP-MS, inductively coupled plasma mass spectrometry, and optical emission spectrometry analysis at KU Leuven. The ICP analysis, too, could not discern any groups within the ENCOME sample set with the same archaeological and contextual categories. In summary, then, the large cloud of data produced by each method for bulk chemical composition arguably supports the notion that the same or similar raw materials were utilized among different workshops or producers. Turning now to the experimental component of my PhD, which was designed to provide useful analogies for the potting practices potentially employed by the late Bronze Age potters at both ENCOME and Iosizomynos. With my supervisor, Dr. Dikomitou Eliadou, and Senior Geological Officer, Dr. Zomeni, we were able to sample around 9 sediments and 2 sands from the area around Iosizomynos, along the Alikos and Yalias rivers. Of the sediments that we collected, only 3 were actually suitable for pottery manufacture, and those include samples 1, 6, and 7, which would be 1 marl and 2 alluvial clays. 2 sands were also selected for experiments with tempering, and they include 1 alluvial sand rich in basalt and dolerite and clinopyroxenes, and another one from a modern crushed limestone quarry sand as a kind of control sample. All of the sediments were fired to a fixed range of temperatures, and a few were tempered with these sands. In terms of firing, the marl in particular, sample 1, demonstrated a loss of optical activity around 800 to 900 degrees, including the decomposition of its carbonates, along with SEM imaging of the archaeological and sediment samples, which I unfortunately don't have time to show you today. Both of these methods and their results corroborate the higher and lower fired subgroups of A1b and A1c from ENCOME. Whether or not the higher fired group achieved temperatures above 900 degrees was not really possible to determine without other methods of analysis, such as XRD. In any case, the effects of firing on the marl were directly comparable to the archaeological ceramics and were useful for identifying technological differences, the implications of which could back up the argument again for multiple producers supplying ENCOME. Moreover, the addition of the sand to the experimental briquettes was also supported the argument for late Bronze Age potters tempering their clays at these 2 sites. And at Iosizomynos in particular, the inclusions were remarkably similar, as you can see in the top left photo micrographs. So to conclude, the results of my PhD seem to support the idea that there was a zone of resources, making a place for sharing of recipes as well as raw materials, and that several workshops or producers seem to be active around and supplying the site of ENCOME. There is further support from the experimental study that potters were tempering their clays with river sand as well, specifically. And importantly, as my PhD was aimed at examining changes in recipes during the introduction of a new technology, in this case the potter's wheel, the results suggest that the introduction of this new technology did not impact the recipe. Potters who were hand building and those who were wheel fashioning used the same clays and or recipes. There was also an important methodological takeaway, which was that petrographic analysis was able to distinguish ENCOME from Iosizomynos or coastal from inland regions. Some open questions remain, for example, concerning the nature of the relationship between Iosizomynos and ENCOME. It's likely that some pottery from eastern Cyprus or workshops nearby were transported to Sizomynos, and as to whether this implies a political or other type of relationship between the sites, I think is still largely up for debate. And as I mentioned at the start, previous research has tended to focus on the study, composition, and distribution of finer wares, but as my research may hopefully flag up, is that utilitarian pottery such as plain white, red and black slip, and plain white painted wheel-made ware, they were moving around too, and are just as important for interpreting ceramic developments in ceramic technology on the island. Thank you for listening.
Thank you. Thank you, Dr. Minos. We have, I think, 2 minutes for questions. Anyone? No questions?
Hi, Chase. It's Eleni Nodaro.
Hi.
Just a quick comment. If I'm not mistaken, you talked about the pithoi, and you said that they were refining the clay. Because
yes, I mean,
apparently you do have deposits that are fine already. So why would they need to refine them? Unless I didn't get it right.
No, you're right, and the issue is that the Nicosia marl, which is one of my experimental samples, is extremely fine. It does match very well the pithoi, but some of them are even finer. I couldn't show you many of the micrographs, but some seem to be a bit finer and have even less inclusion. So it's a hypothesis. I don't have enough samples really to confirm that. I only took, I think, 6 or 7 of these pithoi fragments. So more would be needed and to really explore that. And experimental work too would help.
Great, thank you.
Sure.
Okay, we can move on. The next paper is entitled Chemical and Petrographic Characterization of Early Iron Age Pottery from Los Alcornes region, Western Andalusia, Spain. And it's a paper by Michal Kruger, Violeta Moreno Mejias, and Dirk Brandherm.
Thank you. I would like at first place to thank the organizers for kind acceptance of our paper. All right. I think that here I can. All right. Thank you. The aim of this work is twofold. First, we would like to obtain basic archaeometric data on the clay fabric, temper, and elemental composition of both locally produced and foreign pottery from Los Alcornes region. And second, to demonstrate that even ceramic materials lacking precise contextual archaeological documentation can provide valuable information through archaeometric methods. Dating to the early Iron Age, the corpus of pottery under study was largely recovered by George Bonsor during late 19th, early 20th century. While the majority of our artifacts are different contextual information, they represent the only extant archaeological material available for research, given the scarcity of later excavations at the pertinent sites within our period of interest. The significant exceptions are sites like La Cruz del Negro or Campo de las Canteras. The lack of archaeological context and documentation rendered the material of minimum value, making it eligible for sampling for partially destructive methods such as thin sectioning for petrographic analysis. The sampling was conducted in the Archaeological Museum in Seville, and thin sections were prepared at the Institute of Geology of the Adam Mickiewicz University in Poznań. Los Alcornes is a geographical region in southwestern Spain located in the province of Seville in Andalusia. It is a low limestone hill range situated on the left bank of the Guadalquivir river. This region was particularly significant in the early Iron Age, becoming a key area for the establishment of numerous burial grounds. The Los Alcores Ridge is most renowned for its funerary landscape dominated by tumuli. These elaborate burial structures are furnished with rich grave goods. The presence of luxury items bring orientalizing influence attests that the local elites were active and powerful participants in broader Mediterranean exchange networks. Here you can see Los Alcores in the distance from the Phoenician sanctuary in El Carambolo, and in the foreground Seville, the capital of Andalusia, is visible. The fundamental geological structure here is a high plain. The massif, which forms a characteristic range of plain hills, is composed of successive layers of marine sediments from the Miocene era. The research focuses on wheel-thrown and handmade pottery from 10 archaeological sites located in Los Alcores. Alcaudete, Cristo de la Sedia, Túmulo de los Vientos, Torrevuelo, Entremalo, Acebuchal, Ranilla, Cruz del Negro, Campo de las Canteras, and Gandul. The selection of ceramics was intentionally targeted to represent a range of technological traditions. The analytical corpus comprised 23 samples. Despite the limited number of samples, the analysis remains valuable as they provide unique petrographic and chemical data that would otherwise be missing. The selection of material for analysis was based on the representativeness of artifacts within Tartessian material culture. The subsequent analysis was performed using handheld XRF, Drucker Tracer 3SD, and a polarizing microscope Motic 310. The spectrometer was configured with the major Madrock analytical mode, operating at voltage of 25 kilovolts and a current of 15 microamperes. Each measurement was performed under vacuum with a time of 15 seconds. This configuration optimizes the detection of a range of elements from magnesium to barium. At least 3 spot measurements were taken on an external surface of each sample. Then the mean and standard deviation were calculated. The next 10 slides present samples from specific archaeological sites along with their chemical and petrographic analysis results. However, due to the limited number of samples, statistical tests were not conducted. Instead, the results were compared directly between samples. So here we have Acebuchal, Túmulo de Ranilla, Cruz del Negro, Campo de las Canteras, Gandul, and this is the table presenting all the samples. First of all, the analysis revealed that chemical data are correlated with the distinct manufacturing techniques, which confirms a direct link between production technology and ceramic fabric. Of course, this is a well-known fact, confirmed also during the previous studies. The wheel-thrown pottery group exhibits chemical diversity. This is particularly evident in the varying concentrations of elements such calcium, ranging from 1% in sample 6 to 18 in sample 38, and potassium, notably low in samples 38, 115, 122, and 121. You can see here that the range of potassium is lower than in other wheel-made samples. A low potassium content is a characteristic feature for pottery from the Cruz del Negro site, located in close proximity to the major orientalizing settlement of Carmona. This phenomenon has been previously identified and published in the UISPP journal 6 years ago. The data gathered in the present study corroborates these earlier observations and provides an indication that Carmona was a production center for pottery utilizing specific clay deposits. The three distinct petrographic groups were also identified. Petrographic group 1 is characterized by calcareous paste. The fabric is identified as a bioclastic packstone with a predominance of microfossils and a possible temper of meso-rounded quartz. The mineral assemblage includes the presence of limestone, quartz arenite, muscovite, and plagioglaze. The fabric is typical of the Los Alcores region and is commonly associated with wheel-thrown vessels, especially bowls and Cruz del Negro urns. Petrographic group 4 is defined by a dark brown calcareous paste containing a temper of poorly sorted quartz within a fine-grained matrix, exhibiting a bimodal grain size distribution. This fabric is consistently associated with handmade forming techniques and has been specifically linked to cooking ware from the reference site of Setefilla. In Los Alcores region, this group is represented in Alcaudete, Cristo de la Sedia, Ranilla, and Gandul. Petrographic group 8 is characterized by a coarse-grained matrix tempered with a very poorly sorted coarse fraction of igneous and metamorphic rocks, alongside frequent macrobiotite and polycrystalline quartz. This distinctive mineralogical composition, rich in biotite and rock fragments, could be related to the geology of the nearby Sierra Morena boundaries. This fabric is typical of handmade pottery from the site of Setefilla, and in Los Alcores it is attested nearly in all sites: Túmulo de los Vientos, Entremalo, Acebuchal, Ranilla, Cruz del Negro, Campo de las Canteras, and Gandul. To conclude, despite being based on a scarce, numerically limited, and often poorly contextualized archival assemblage, this study provides insights into pottery production in Los Alcores. The analysis confirms the presence of local bronze and late Bronze Age ceramic traditions originating from the Sierra Morena area, identified through specific clay recipes for handmade fine wares, Petrogroup 4, and utilitarian cooking ware, Petrogroup 8. Furthermore, a distinct foreign tradition is evidenced by Petrogroup 1, a fabric characteristic of Los Alcores that is strictly associated with wheel-thrown pottery. The chemical signature of this wheel-thrown ware, particularly its low potassium content, aligns with the previously established data from Cruz del Negro. This correlation strengthens the hypothesis that Carmona region, northeast of Los Alcores, functioned as a production center for wheel-thrown pottery during early Iron Age. Thank you very much.
Any questions, please? May I ask something?
Yes, of course.
I didn't get it immediately. Your calcareous pottery, which is not very much.
Yes.
Which group does it go with? The handmade or the
the
wheel made?
Wheel made, exactly.
Only the wheel made.
Wheel made. Yes.
Does it have to do with decoration? Probably that it helps the decoration better, or it's just. Why do you think this is?
I think it is related with the manufacturing techniques. At the beginning of early Iron Age in this region, the potter's wheel is introduced, and this petrogroup is used for working with potter wheels. So the grains are very small. Calcareous paste is there, so it is used for
so
this.
So it's an innovation that comes with the wheel.
Exactly. Yes, it is. It is.
It's very interesting. Thank you.
Oh, please.
Any other question, please? No? Thank you. So we can move to the next. That was for you. So the next paper is again online. It's Iron Age burial rituals, symbolism and technological ceramics analysis from the Arkavathi Valley, South India, and it's Kumar Praveen that we have online.
Yeah, thank you, respected chairperson, distinguished scholar and fellow delegates. I am Dr. Praveen Kumar K, Assistant Professor, Dr. Hari Singh Gaur University, Sagar, Madhya Pradesh, India. It's an honor to be presenting my research in this distinguished UISPP 2025 Colloquium. First of all, I would like to apologize if I'm not reaching you through my language, since I'm speaking in Indian language. My paper title is Iron Age Burial Rituals, Symbolism and Technological Ceramic Analysis from the Arkavathi Valley, which is in India and part of India, southern part. Focuses on understanding how technology, ritual symbolism, and social identity are reflected in the ceramic traditions of the Iron Age in southern Karnataka, which is the study region for this research. Respected delegates, the study integrates field archaeology, petrographic thin section analysis for the first time in the study area, and microscopic examination to identify the technological choices, mineral compositions, and firing techniques which were used by ancient Iron Age potters. I particularly focus on two sites called Savanaturga and Nagamangala, which represent a distinct social settings. The ritual or agricultural context or elite context at Savanaturga, and the agrarian domestic context at Nagamangala. So through this presentation, I aim to demonstrate how ceramic technology can serve as a key to understanding socio-cultural differentiation during the Iron Age, and to show how scientific analysis such as petrography can enrich archaeological interpretation in Indian context. Before I begin the presentation on archaeometric ceramic analysis for this session, I would like to highlight an important contextual aspects of my study. The pot sherds, whatever we selected for this research, come from the burial context, as well as from the, we have actually access from the museum and also recent field data. This means that these ceramics vessels were intentionally placed within the graves as part of the mortuary practices, which are reflecting not only technological traditions, but also social and ritual meanings which are associated with the individual buried. Understanding the burial context, which can help us to interpret how these ceramics were used, not just as everyday utilitarian objects, with the individual, but as a symbolic artifacts within funerary rituals as well. In addition, before I start, we'll also, in the main major work that is petroglyph associated with the same archaeological setting. So these rock carvings provide a valuable insights into symbolic expression as well as relate to the same belief system which can be reflected in the burial ceramics. Before I start, I'll begin with a brief overview of the region and research objectives followed by the analytical methods, petrographic result, and their broader cultural implication. So thank you for your attention. I'll now begin with the presentation. The Arkavati River Valley, which is located in the near Bengaluru, Karnataka, is a famous IT sector, which is a very rich archaeological zone for Iron Age research. These two sites were actually selected called Savanadurga and Nagamangala, distinct and interconnected sites on the Arkavati Valley. These integrates field archaeology with photographic and microscopic analysis for the first such study in southern Karnataka. And also whatever I'm going to present, these are the preliminary analysis, analytical report. And also we are taking into further more detailed scientific analysis for the materials. This is the location. And regionally, Arkavati, these are the two sites we have selected. And the main objective of my research to document and classify Iron Age ceramics assemblages in those sites, and also to identify firing techniques, mineral compositions, and symbolic roles in the ritual, and applying petrography and microscopic analysis to understand technology and raw material sources. And before I start, I should tell that the area why it is very important, and also geographically, the Arkavati River Basin, which is located near Bengaluru, Karnataka, and the Savandurga and Nagamangala, which are around 12 kilometers from Magadi town. Geologically, this is a very famous geological features it has. Especially this is called granite, Enger granite series. You can see this, the red patch. This is come from around 250 kilometers towards southern part, and the study area is located in the particular area where we can see the major archaeological sites, especially the Iron Age burial complexes as well as settlements. Hydrologically, Savanadurga, and it is located on the Arkavati, and Chikkatore Halla, Nagamangala, and Bhargavati Vale. It is very close to the main river catchment. So mineralogically, this area is actually composed by quartz, granite fragments, and minorly mica, which are suitable for ceramic production. So this is the geological map of the area. You can see this. This is the stretch which come from around 250 kilometer stretch. It is called a Enger granite series. It's a very world famous geological formation in study area. So now I'm coming to the site Savanadurga, which is a major site which is situated on the right bank of Arkavati River. And this was a very famous and first excavated by Branfield in 1881. One of the earliest Iron Age site excavated in South India as well as entirely in India. And recently, for my doctoral research from 2016 to 2023, I re-investigated and also documented around 56 burials, and recently again we visited and we collected some samples for analysis. And symbolically, these burials linked to hunter or elite or warrior group based on the material analysis from the museum and random collections. So these are some illustrations. So where the Branfield was excavated and illustrated the burials. And the second site, and this is a very interesting that the pottery which were collected from the burial during the excavation by Branfield, very unique ritual pottery were actually kept in the burial, three-legged tripod jar. It is especially for storage in grains. And also in this, the Branfield was identified organic material, remains over there. And very interesting that two hollow horn-shaped terracotta objects, which maybe they were actually used for storage in honey or medicine kind of things. He was interpreted in that manner. And high-neck globular pottery. All these are actually produced during the excavation and also which are kept in the museum. So we have collected some samples through the museum as well as recent investigation. So this is the site, so the catchment, so where we can see the river catchment as well as the sources for the pottery, pot making. And the second, this is the results. So where we can see the burial documentation, around 56 burials. Another site, Nagamangala. This is located 5 kilometers from Savanadurga on right tributary of the Arkavati, around 59 burials. Again, we first we discovered this site 2017. Here, so we found coarse redware and sickle blades and ceramics, other remains, and also cremated bones as well. So it represents an agrarian or subsistence community which is differing from the Savanadurga hunter community. So these are the materials we collected for the this one, the Nagamangala, the site name called Nagamangala. So this is recently we visited and we collected the samples. So we, badly it was destroyed by treasure hunters. So this is the settlement pattern, how we are actually understanding the settlement pattern of the particular Nagamangala region. So without wasting much time, I'll come into the main analysis of the my research. The petrographic and microscopic analysis, which performed using thin sections under PPL and XPL. This study is for grain sorting, examined for grain sorting, mineral inclusions, metric texture, and firing features as well as porosity. So now I'm moving to the samples, so which are collected for. I have chosen 4 samples. Still, this research is ongoing. So we have collected 2 samples. From 2 samples from Savanadurga and 2 samples from Nagamangala for this analysis. The petrographic analysis which are yielded the insightful result on ceramic technology and functional differentiation between 2 sites. One is Savanadurga and Nagamangala. Starting with Savanadurga, this is a very interesting that redware jar. It is a thin section which is revealed a coarse and gritty fabric, which is dominated by quartz and granite inclusions, and firing appears to be medium oxidized, which is indicating open kin firing with the partial temperature control, and the texture and mineral composition suggests that it was a domestic or storage vessel, but it was kept in the it was also used in the burial ritual likely used in daily activities as well. Second sample is another redware type but coarser, which contains a quartzite and feldspar inclusions. The firing pattern shows uneven oxidized, which implies a non-uniform heat exposure. And in contrast, Nagamangala 3, the sample, this is a blackened redware bowl. So fine thin, well navigated clay fabric, with the quartz and feldspar minerals, and firing is a very controlled at medium temperature, which achieving the characteristics black and red ware surface. And especially in India, we have black and red ware, especially in the burial context, used in ritual or special ceremonial context. And finally, the Nagamangala, the sample number 4, red slip global vessel, which is display medium coarse but well fired texture with a visible red slip on the interior, and mineral composition that is dominated by quartz and iron oxidized. And these are the observations in the analysis of thin sections. And as I already told that the Savandurga, the site, it is a coarse matrix, unsorted grains and visible temper. It is an open firing evident from uneven oxidation zones. So this is the result of the qualitative petrographic parameter of 4 ceramic samples, 2 from Savandurga and 2 from Nagamangala. Starting with, we see poor grain sorting and coarse metric with abundant mineral inclusions like quartz and granite fragments. And also the porosities are very high, and firing intensities are very medium. Maybe these indicators point to less refined clay preparation and open firing condition. So that's why we could see, the thick text section. And the sample 2 shows a moderate sorting, and the coarse metrics are still rich in inclusion, but with a slightly improved fabric control compared to Savandurga sample 1. And I'm coming to the another sample, black and red ware from Nagamangala, which displays a good sorting, moderate inclusion, especially that is a vessel and a black and red ware bowl, and a very smooth and matrix texture, and a very low porosity, and controlled firing, which indicates careful navigation and deliberate thermal management. Red slip global vessel I chose for analysis, that is exhibits excellent sorting, fine inclusions, and a compact matrix with low porosity, and the high firing intensity and fine control of oxidation. And now I'm coming to the this is aesthetic purpose, and which aligning with its decorative and ritual association. So now I'm coming to the interpretation, technological interpretation. So as I already said that Savandurga and Nagamangala. Savandurga is a high quality and fine and well fired wares for ritual or elite context. Nagamangala, this coarse utilitarian wares linked to everyday agricultural practices, because based on the result and also identification of the cultural materials, we are actually coming to the point that the Savandurga, the population and occupation is a different, and Nagamangala, the Iron Age societal occupation is a different. So evidence of deliberate oxidation, which is reduction control, and clay navigation and surface slip preparation. So finally, this suggesting that indigenous ceramic technological advancement, and we never seen any, geologically this area is already, as I mentioned, so highly concentrated by crystal as well as granite, and also including dolerite dike, but we did not find out in the section analysis dolerite dike. So that's why it's locally whatever the geologically the materials available, they used for making these potteries. And another synthesis culture, especially first ceramic technology, which can be mirrors a social and occupational differentiation. So that's why the Savandurga, which is symbolizes a ritual martial group, while Nagamangala represent agrarian practices. And the ceramic, which embody both symbolic expression as well as technological traditions of the Iron Age, which are indicates shared cultural framework at functional diversity within the study area, that is Arkavati Valley. Now I'm concluding my research. This is first integrated petrographic and microscopic analysis of the Iron Age ceramics in southern Karnataka. So still we are actually working for more samples associated with Arkavati Valley in more than around 5 more sites for the upcoming research, and which are overallly what I could say that this result reveals local technological knowledge, ritual symbolism, and resource adaptability from the river as well as from the nearby the settlement, which highlights the regional distinctiveness of the Arkavati Basin within South Indian Iron Age archaeology. Thank you very much. If you have any comment on my research, please.
Any questions, please, for Professor Provine?
Yeah.
Thank you very much for a very interesting talk. I have 2 questions, if I may. First is, you're talking about the Iron Age in this period. What are the exact dates you're referring to? And the second, if I understand correctly, you claim the existence of the hierarchical societies. So if it is the case, can you see other signs, for example, the large burials or some deliberate metal working or any other signs of the highly hierarchical or just hierarchical society? Thank you.
Yeah, thank you very much. I forgot to talk about the chronology and time period of the Iron Age culture, which is from the Bengaluru region. So based on the carbon dating nearby the sites and the comparison with the cultural materials, and also one burial was actually, during the excavation, the Branfield. So he discovered a coin that is belongs to Roman. There is also says that it is connected with the early historic context, but based on the ceramic analysis and the typological analysis with the neighboring excavated sites and other sites, this is generally we are actually keeping the date for 600 BC to 100 AD. And second point, you asked hierarchical status. Based on the cultural materials which were discovered from the burial, especially arrowhead, dagger, and sickle, which is symbolically representing that agricultural implement. So based on that, we are identifying the burial depth. This is belongs to, might be, he was a hunter or agrarian family.
Any other question? No? Thank you so much.
Thank you very much.
So we now proceed to the last paper of this session by Knut Goharbin and Omid Udbashi, entitled Reassessing the Tariq Hanech Mosque of Damghan, an interdisciplinary approach to chronology and material analysis of the bricks in an early Islamic building in north-central Iran.
Okay. Thank you very much.
Go Harbin.
Good afternoon, I think. Good afternoon, yeah. And unfortunately, my colleague Behnut couldn't come and present because he was the leader of this project, and I'm here to present this project and the results. I talk about one of the earliest. Is okay? Thank you. Good. Is one of the earliest mosques in Iran that has been dated to the second, third century CE. That its name is Tarikhane, is located in north central Iran in the city of Damghan. That Damghan is one of the oldest cities in the Iranian plateau that we can see some signs of settlements and also urban developments from the 4th millennium BC onward, and also one of the most important Parthian and Sasanian regions in the Iranian plateau, but you can also see some of the early and middle Islamic buildings in the city. But Tarikhane Mosque is in fact located in Damghan, and somebody believe, based on the early excavations and the studies on the Islamic architecture, they believe that it has been constructed in 8th or 9th century CE in the time of Abbasid Caliphates, and its style is very similar to the late Sasanian and other early Islamic buildings and mosques, and also some of the Sasanian palaces. And this is one of the newest documentation of the site, and you will see that it has a minaret here at the right one. I don't know, you can see it, but it's in the right. It has a minaret that it has been added to the building later, but the main building is a very typical mosque in the early Islamic periods with a columnar hall. And the objective of this research was about the study of the building materials, masonries, bricks, and also dating, and also development of the research to do some assessment, conservation assessment, and the final, at the end, in fact, proposing a conservation and restoration process and decision making for that building. This building has been, I should say, suffered some wrong restorations about 60 years ago. And when they started working on this building, you can see in the right upright that the building was higher and the form of the arcs was semicircular. But after doing some restoration, the building was lower. The height of the building was decreased, unfortunately, about 60 years ago. And the shape of the arc was changed. So it means that we cannot trust the upper part of the building for any archaeometric and also dating aims. So we I will show you that we just selected samples from the columns, not from the arcs, upper part of the arcs. Another thing that was very important in this issue was the size and shape of the bricks. And I mentioned before that there is a very important Sasanian palace close to this site in southeast of Damghan city that they call the Tepe Hisar, that it has been occupied as a settlement from the 4th millennium BC onward, but also there was a very important Sasanian palace, and we did some comparison between the size of the bricks between this building and that Sasanian palace, and we found that they are very similar. You will see that in general there are about 35 in 35 centimeters in 6 in general, but some of them have some outliers, but in general we can see that the main size of the bricks are 35 to 5 to 6 centimeter. And also another thing was the arrangement of this type of bricks in the columns, and you see that there is a very typical form of brick arrangement in the Sasanian period that has been used in the early Islamic period too, that we call it khofte and raste, or teflisi, that it related to Tbilisi in Georgia, and we call it in Iran teflisi arrangement. And you will see that this type of arrangement was found also in excavation of Tepe Hisar Sasanian palace. And it shows that this brickwork and construction is completely under influence of the Sasanian period brick construction and brick building forms, and you will see some of them also here and the right up. This is a khofte and raste, this is up and down, something like that. And also in the one of the main columns in the left, We'll see that. And also we'll see that the size of the bricks in another Sasanian site in northwestern Iran was completely similar. 35 in 35 in 6 in general, with some small differences. So there was two hypotheses for us, that maybe this building has been constructed in the Sasanian period, but its function has been changed in the early Islamic period. Or maybe the early Islamic architectures, they tried to continue Sasanian brickwork. And then we started analytical techniques to use thermoluminescence dating and mineral chemical analysis on the bricks and also on mortars. And firstly, we selected 4 samples from the different columns, from mortars and also from bricks. And also we took 2 different samples for luminescence dating, because there was some differences between these 2 parts of the building. And the thermoluminescence showed us very interesting results. The first one that comes from the central part, the green area, is from the 8th century CE, 2nd century AH after Hijrat, and it shows that is one of the earliest examples of mosques in the Iranian plateau. And also the left part, the red part, showed us some change in the 14th century CE from the Mongol time, from the Ilkhanid period. And it shows that this building has not been constructed in the Sasanian period, but has been constructed in the early Islamic period by a Sasanian manner. And then we moved to analysis of the microstructure and chemical composition of the bricks, and we found that the bricks, the 3 samples that we analyzed, they have very similar microstructure based on the scanning electron microscopy, and very similar chemical and mineralogical composition, especially high percentage of SiO2 or high percentage of silicates based on the semi-quantitative XRD analysis. And their XRF analysis also showed very similar composition, but there were some differences. 2 of the samples, they showed under-fired, maybe low temperature firing, maybe about 600, something like that degree. And one of them showed a little bit higher, about 700, because we could find some sintering in its microstructure. Most of them are silicates, and their composition is similar. They might have been made by local sources, but it was not a part of our research, but could be very interesting if somebody can, or if we can continue this research on the resources of raw materials for brick production. And also we could find some evidences of effect of gypsum mortar on the structure of this bricks, because of high percentage of sulfates, and also some evidences of colorite from the salt efflorescence. And also we could find some very interesting things in difference between different types of mortars and plaster. Here, for example, in some of the vault mortars that are modern, we could find that they added high percentage of clay and soil particles, because they wanted to it be cured and settled quickly. But in the plasters, they didn't use that, and you will see that is more homogeneous structure in the plasters. And also in some of other wall mortars, we couldn't find any evidence of high percentage of clay or additions, but also we found some dissolution in the structure of the crystals. It could be because of their in fact, they contact with water for a long time, especially if the samples were from the down part of the columns. And also the slurry mortars, you will see the structure of the gypsums are completely coarse, and it shows that they had long time to be set, longer than the mortars. Maybe if the mortar is about 8 to 10 minutes, it will be about 20 to maybe 25 minutes, something like that. And also we could find in the mortar that the brick joints was similar. In fact, they used different types of mortars and gypsum. In fact, gypsum mortars and plaster for different aims and purposes. And these are the composition of the mortars. You see that they are not very similar. In fact, some of them have a higher percentage of silicium or some other elements that they come from the soil additions, and in their also in their mineralogical composition you see that some of them show some bosonite beside gypsum, and it means that because they didn't fire gypsum in a very homogeneous kiln, some part of the gypsum was in fact changed to bosonite, some of them didn't change, and some of them after adding water came back to gypsum, but some of them maybe have been affected by the environmental situations, or maybe have not been completely mixed with water to make gypsum at the time of preparation and setting. And in general, for the mortars, I can tell you that the composition are gypsum based, and some of them have been in fact changed and improved by adding some inorganic additions, especially soil, but some of them, they just have some impurities. This is because of, we can see some of them have high percentage of silicates, high percentage of calcite or something like that, but some others, they have not a high percentage of these additives, and it probably shows that this gypsum has been provided from the local in fact resources, because in Iran you can find local gypsum resources everywhere, from the north of Iran to south, and from west to east. Is very accessible material for construction and also preparing mortar and plaster. And some examples, they showed maybe addition of some lime because of some specific purposes, especially the main purpose could be due to controlling the setting time of the mortar on plaster. Thank you very much.
Thank you, Dr. Bashi, and sorry for wrongly introducing you.
It's very hard also for Iranians, no worries about that.
Your name's okay, the first one was a bit more difficult. Okay, if there are any questions. Please.
The presence of basonite is very strange because it's a long time and it's very reactive to the So I wonder whether this is an effect of preparation of the sample. It's very quick, especially in diffraction. When you powderize and grind, you produce a little bit of basonite. And you know, I would be very careful in saying that there is basonite from 800 years. Yeah. And the other thing is, I'm very curious about the lime addition to gypsum and the clays, especially when they are all together. Do you think that they produced lime and then they were adding clays for a sort of pozzolanic material, or the clays were heated together with the lime?
Thank you for both questions. For the basonite, we also saw the evidence of this problem, in fact, I think, in some older buildings in Iran, especially when these buildings are located in very high temperature regions. And because, you know, when they powder it and they add water and they start to preparing it, all of the gypsum will be mixed with water, and having basonite again is a little bit strange. But we saw that when the building is under effect of some high temperature, not 150, but maybe 50, 60, but for a long time, you can see some evidences of basonite. We saw that in Haftepe from 3,400 years ago, and Haftepe is in Khuzestan in southwestern Iran, and the temperature goes to 60 degrees, and for a long time. It's not very high temperature for changing, but it was so strange because we saw that. Another thing could be if they prepare this paste or this very high viscosity paste, they added at the end, they added some powder to that, but they didn't mix that. I'm not sure about this. Why? Because at this moment we have traditional gypsum preparation in Iran. They have some masters that they use that they don't do this. but presenting basanite in different types of, all types of gypsum stuccos, gypsum mortars, and also gypsum plasters in different archaeological sites that they have been out, have been excavated for a long time, or they have been in outdoor environment, is very strange, but is very common. I think the only thing could be effect of temperature, because this building has not been heated about 150, 180 degree, but just maybe 60, 70, maximum 80 under sun, you know. Could be, but I'm not sure that is possible. But we could find basanite not only in this building, but can give you more than 10 examples of gypsum materials that have been exposed to sun for a long time. And for the second one, because most of these resources, they have impurities of clay. So in some cases, they heated them when the impurity is low. But also when they want to make some mortar and they need to use that for quick setting, they add deliberately, but they don't heat that. You know, they add it after they prepare the gypsum powder. So if this is very low is impurity, it has been heated about 200 degrees or less together, but if it's very high, no, they added that after.
Thank you very much for a very interesting talk. If I understood correctly, the chemical composition and firing conditions of these bricks were heterogeneous. How does it affect the color of the bricks?
Thank you. Thank you for the question. That one that was suffered, in fact, higher temperature was yellowish, but the other one were about a little bit reddish, and also the percentage of iron was higher in two samples that they were reddish, and they were in fact they were heated, in fact, in lower temperature. So I think I think it's better to say that the higher temperature led to a little bit more yellowish, creamy. But in general, when you look at the building and the bricks, you will see from reddish to yellowish, both of them.
Any other question?
Thank you. You said the basanite development was due to the insulation and the temperature over hundreds of years. So did you see any difference in the plaster or in the mortar, in the front side and in inner side composition of that gypsum-like mineral, or can't you look at that problem?
Yeah, thank you. Yeah, in general, yes. Generally speaking, I should say that in many different buildings that analyzed, because some of my colleagues are working on gypsum plaster and gypsum mortar, and I'm collaborating with them, we saw that when the building, the area of the building, the wall or something like, is under sun and a higher temperature, you can see some basanite. Not too much, in fact, just some basanite, you can see that. And also it was interesting because we could find basanite in the microstructure under the scanning electron microscope. Not only when we looked at the crystals in secondary mode, but also when we did some analysis on the cross-section by backscattering mode, we could see this difference of composition. It's not very clear, but if you change some of the imaging modes, you can see that. And yeah, in general, I should say that in outer part of the building, sometimes you can find basanite, but not in the inner parts.
No other questions? So, thank you very much.
Thank you.
And thank you all. Lunch break. Now it's lunch break, as I see in the program, until 2:30, when we will continue with metals. Okay.
Okay. We'll continue with metals. Metals. Unfortunately, I will be alone in the table. As I see, the following 4 papers focus bronze and copper. First paper is Provenancing Tin in Bronze Age Italy, the state of the art. Gilberto Artioli, Ivan Angelini, Daniel Berger, and Caterina Canovaro. Please keep the 50 minutes. Not 50, 15.
Right. Okay, thank you very much for allowing the floor. This is, yes, so I'll talk about tin source, and of course from the literature point of view is the old Cassiterides that's been gone for forever. What I found is this review of the textual, and I'm not quite sure because it's all in Spanish, how and which text actually she derived the roots from Iberia and Cassiterides, but this is roughly, this is the textual evidence that was provided. Of course, the history of tin, the tin problem goes back to the Dayton Wertheim Muli discussion, and has been treated in at depth with scarce data in the past. And finally, we had this tin project from Germany trying to apply tin isotopes and trying to sort. We have the starting of the tin in Mesopotamia in the late 4th, beginning of the 3rd millennium. Then we do have the extensive use of bronze extending from the Persian Gulf to the Aegean. And then we have evidence from the 3rd millennium in the European Bronze Age. We certainly know when bronze arrived in Italy. We have evidence from the Lavagnone. We had this dagger that is one of the very first bronze objects in Italy, dated to the BA1B. That Ivana analyzed a long time ago. But we also did, there are logs in the Lavagnone. We analyzed all the metals in the context, and we see clearly the tin appearing in the soil, around 1700, 1800. So this is really the first tin coming to Italy, and calibrated. We also see that there is previous metallurgy, but not bronze, from the same area. We know that. Now, the 2 major sources of tin, which also correspond to the available deposits nowadays, are from the Atlantic province, which includes the Erzgebirge in Central Europe, and Far East Asia, including China and some Kyrgyzstan and Central Asian deposits. Now, in the past, there's been a lot of discussion on Sardinian, Tuscanian, and Anatolian tin, even some proposal for Balkanic tin. They have not been used in the past. I don't have time to go over that, but clearly they are out of the question for the Bronze Age. So the 2 major sources can be distinguished by lead isotope and tin isotopes, possibly. There are a lot of discussion yet. The Atlantic province, including Erzgebirge, have an old geological age between 360 and 280 million. So it's, let's say, old deposits, Hercynian, from the Euro-American plate. And then all the rest are basically linked to the Alpine Himalayan orogeny. They have a much younger age, which is about 50 million age. So they can be, in principle, distinguished by the lead isotopes, which are useful to date the deposits and the rocks. So there are, this is a summary from a recent publication of Powell's, and you see that there are these distinguishing ages of the deposits. Now, what did we analyze with respect to what is being published by the two main groups working on that, the Cesa Mannheim group and the Powell group? We analyzed that there is this ingot from the Parma Terra Mare and a filament and few droplets that we think they were ornaments, and during the firing of the body, it was melted and formed these small droplets in the soil of the necropolis from Alba. And then we have these two Padada jugs that I presented a while ago in the Oroli Festival. And then several ingots from Sarco Esporos, Villa Grande Stresaili in Sardinia, that we analyzed a long time ago, and a new ingot, or I don't know exactly what it is. It's a very strange object in Salina and in the Aeolian Islands. So these are all pure tin objects, because you cannot analyze the lead isotopes in bronze because copper is overwhelming the signal, so you really need pure tin in order to do that. We also have the tin isotopes made by Berger and Cesa for all of these items. And if you take a look at this blue arrow is the signal of most of the objects. Two of them are a little bit lower, and you see that the tin isotopes indicate clearly the Atlantic provinces for these things. This is the suggestion. Sardinia is out of the question. Mushiston and the Tajik mines are out of the question. We can discuss about Iberia and Brittany a little bit with respect to the other one. The lead isotope are also problematic, like the tin one, because they are very radiogenic. One signal is dominated by uranium, the other signal is dominated by thorium. And, but if you plot all the available data, you see that the 207, 204 is actually clearly indicating different age from the Asiatic deposit. The problem is that we don't have enough data from the Asiatic cassiterite. So we can extrapolate, but while the Atlantic province is very well defined, the other one is dominated by the Chinese data. That's not enough to determine the isochron. But the other very interesting thing is that all of the data, apart from two, that we have from Asia demonstrate that they are very devoid in thorium. And the curve is almost flat, which is very interesting, which I think is one of the parameters we can use to distinguish the Asiatic tin with respect to the Atlantic one. So if you plot in this ore data everything that we know, this is, it's been published several times, all the ingots from the Eastern Mediterranean. You see that they fit very well with the isochron, especially in the 208, 206, with the Atlantic province. Even the ones that are enriched in thorium, which are very few samples, but you can distinguish Uluburun and Haifa and Kafir Shamir. They all have two groups. It's been known for a long time that there are two different groups of items. I think they all fit different parts of the Atlantic provinces between Iberia and Cornwall. In there you also see the ingots from the Salcombe shipwreck and a few other ingots found in Cornwall. They fit all together. Apart from the East European and the Italian items, we do have the Salcombe that I just mentioned, we have Barrio de la Campana, that is in Murcia in Spain. The data are available. If we put everything together, these are only ingots, no ores, you see that they all fit very well. And so basically, if the hypothesis of the Atlantic province from the the Eastern Mediterranean ingots is correct, then most of the items we do find also in Italy and around the Western Mediterranean, they fit very well with this Western source of tin. Now you see that Barrio de la Campana and actually some of the Sardinian ingots are actually streaming out. This might indicate that there are multiple sources within the Atlantic provinces. We don't have many data from Iberia, but also a couple of, I cannot exclude, this horizontal line of Asiatic, for a couple of ingots from Sardinia. So I can't exclude that Sardinia is actually a hub for metals going back and forth in the Mediterranean. So basically, we think even the very radiogenic one fit very well with the Atlantic model. We think that most of the circulating ingots in the Mediterranean are from the Atlantic province, so the theory of the cassiterites is correct, as the text actually always show. And unfortunately, we still miss, more data from the Asian ores, especially Tajikistan. I would love to have more lead isotopes from that. One further element that was published this year is that they published the difference between Cornwall and Esgebilge and Iberia and Brittany. You see indium, even in very low quantity, can distinguish between Cornwall, which has always more than 10 ppm of indium, and Brittany and Iberia systematically have lower. So most of the ingots that we analyzed from Italy are also very low indium, and we think that they come from Iberia more than Cornwall, most of them. So Berger also published a map showing the start of the bronze and the use of tin from Brittany as dates and going in 1700 before Christ in northern Italy, and then going in 1400 in southern Italy. The data that we have from Salina, the data that we have from Alba and Parma, they fit perfectly this model. Okay, I just overlapped our data on this map that has been published this year, and I think that it goes together very well. It was published by Krause almost 20 years ago that the bronze was coming from the north and not from the south. So Sardinian and Tuscan tin were not used. Please scratch that from the literature. Tin in use was mainly from the Atlantic province, and we think from this preliminary data that Iberia for the Sardinian and the tin used in Italy is more Iberian than Cornwall, and we really need more data from the Asian ores. I think that's the picture. Thank you very much.
Thank you very much. It was very interesting. Any question, please?
No, well, part of them we published them in the paper 5 years ago, but we are going to prepare a publication. Our whole, yes.
It will be very interesting for everyone. Thank you.
Yes. Could you go back to the graphs? Here. The next one. Yes. We are, of course, interested in what you say about Mochlos. Where is Mochlos on that chart?
I think it's in the center, more or less. I think these are some of the things. They're really in the group.
Because the one which looks like purple, Mochlos, is over there, I think. Isn't that purple?
I think these are the ones. I mean, I should look at them. I put them together. But
this one, or this one.
No, I think that's one of the Kefar Shamir. I think it's really in the center of the thing.
Okay, because we have several problems with this idea of tin coming from Iberia or from Cornwall, because we have nothing at all coming from the west. But we have a lot of stuff coming from the east, particularly from, you know, Afghanistan, probably Tajikistan as well, because we have lapis lazuli coming from there, and a lot of other objects which we are publishing just now. So for us, it is quite strange to hear that the ingot, the tin ingot we have at Mochlos, which Daniel Berger analyzed, and would be coming from the west. And when we discussed this with Daniel, he actually checked the isotopic pattern of Tajikistan and Afghanistan and so on, and he agreed that Mochlos might come from the east. So well, it's a bit of a difficult question.
It's very discussed, I think, and unless we have a lot of lead isotope data from Tajikistan that we don't have right now.
You mean
of the
tin,
ores.
tin isotope or lead isotope, so both?
Lead isotopes are better than the tin isotopes
I fully
on
agree.
cassiterite. And because you know, they really show, you know, a different trend. I don't say it now. You can really see. Unfortunately, the data that I have are mostly dominated by the Chinese ores because we don't have the Tajik ore. Okay, but that would be anyway. Mochlos is really lying now on the on this line, which is the isochrone of 320 years. So I think that if we really need to go, let me go back and discuss it thoroughly. Then, if you want. Sorry about that. Yes, this one. If we really need, so they lie on a very old isochrone geologically. So if I need eastern source, I would go to the Tien Shan, not to the Tajik ores, because these are much younger. Okay, so I would really need more data from this. This is very similar to this or other things. Okay, so the real discussion should be cassiterite. We need data on cassiterites, not on the metals.
Yes.
In order to compare to clearly.
I've been working with, as you probably know, with the Russian Academy of Sciences, and we did some studies about lapis lazuli coming from different sources and so on. And we're trying to study also the cassiterite. Actually.
That would be great. I mean, if you have lead isotope from cassiterite for the Tajik, I've been looking for geological data. They are not available. You know, I wrote to Russian scientists and they said, well, I mean, they never published this stuff.
Yeah, no, well, it is difficult to find the samples, of course.
Wow.
We found them from the museum in Moscow.
If you have the Tajik cassiterites, I mean, I've been asking everybody, collectors and everything.
I haven't got it.
That would be very interesting.
It would be difficult to get it out of Moscow, but
I know.
But yes, I believe that we need a lot more of data.
Absolutely.
About
but
this.
what we have right now is fitting very, very well with the Atlantic model. Even look at this. This is two samples that Sophia Stoss-Gale published along. Actually, one is Sophia Stoss-Gale, the other is from a Chinese database recently published. You know, they follow different lines. This is high thorium in low thorium samples. And if you look at one of the data from Sardinia is exactly here. Is following this line. So even the anomalous samples within, you know, the model, they fit very well the anomalous samples that from Cornwall and Iberia. So
Yes,
at the
another-
moment, that's what I can say.
Another possibility is we are going to study also some sample from the other ingots we found in Crete, the tin we found at Crete, and so we will maybe know a bit more.
That's
about
fine.
this.
But you know, I would be doubtful a little bit about the tin isotopes because they are too much overlapping. I think
yes,
lead
I
isotopes
agree.
are a little bit more.
I'm sure it
telling.
would be better to do both.
Well, of course.
And a lot of other kinds of analysis.
Good.
Any other question?
Thank you for your talk. I just like whether I'm right that you showed the data from Ascarali.
The data from?
From Ascarali, from the Altai Mountains, from the Kalbanarin tin.
Oh. You know the geological map?
No, the lead isotope analysis of Ascarali, from the Altai Mountains. No?
Sorry about that. I'm going back and forth. This is the lead isotopes of.
Or
most
it
of
was the
things?
tin isotopes, but
Oh, the tin isotopes. This one.
yes, Ascarali. As I understood, that you said that that geologically they are probably the same as with the Mushy stone, but it shows just like much lower, right?
Yeah, Mushy stone is much lower than what we have.
No, Ascarali is lower than Mushy stone.
Yeah, this one.
Yeah, this is. And it's interesting why, if it is the same or geologically. And also I think that we talk about Mushy stone so much. Why we're not talking about one of the largest tin deposits in Asia, in the Altai Mountains?
Oh, this is wonderful. I mean, we need the data from that. Anyway, tin isotopes and lead isotopes are behaving differently from the crystal chemistry of cassiterite.
Of course.
So it is entirely possible that the tin isotopes, which are due to the low temperature deposition of the cassiterite, are actually have lower values. Whereas if they incorporate a little bit of uranium, they shoot up, in the radiogenic signal of the lead isotopes. So they're unrelated geochemical. So that's why the tin isotopes and the lead isotopes should be done, as a complementary information.
Yes. Yes, I understand it. Thank you.
But there is only one point that I think Berger analyzed. I mean, we need a lot more data in order to define the field properly.
Thank you.
Thank you very much.
Okay.
Okay, let's go back to Iran again. Next paper, Prehistoric copper-based metalworking in southwest Iran, inside from the archaeological finds of the Kersham-Beshar rivers basin. Omid Oldbashi, the speaker, Matthias Mayhofer, Reza Nasseri, Seper Bahadori, Javad Tahiri, Marteza Habib Zadeh, and Siavak Soragi. Sorry, wrong spelling.
Thank you very much, Bella. Thank you. I came back. Sorry that you need to see me again. But I jumped from north central Iran to southwestern Iran, and from early Islamic to prehistoric period, and from gypsum to copper-based objects. And I just give you a very short information about the prehistoric copper-based metallurgy in Iran that starts from the middle of the Neolithic period using native copper, and they jump to copper and arsenical copper in the Chalcolithic period, the 4th millennium, 5th and 4th millennium BC, and then came to tin bronze in the middle of the 3rd millennium BC, and continuing tin bronze production and using to end of the Iron Age, the middle of the 1st millennium BC. And the thing that is very interesting about Iran is that you see that in the western Iran, the blue part, you will see that tin bronze was started, I think I need to be here, okay. Started at the middle of the 3rd millennium BC, and beside arsenical copper, and continued using tin bronze into the end of the Iron Age. But in the eastern part of Iran, we have no clear vision about tin bronze metallurgy even at the end of the Iron Age. So it means that maybe tin bronze metallurgy started at 3rd millennium BC in western Iran and developed to the middle of the Iranian plateau in the 2nd millennium BC, but we have no tin bronze even at the end of the Iron Age in eastern part of Iran, from northeast to southeast of Iran. And copper and arsenical copper are the predominant materials from the beginning of copper-based metallurgy to the end of the Iron Age. But I jump here to the southwestern Iran, in a region that we call it, the modern name is Kohgiloye and Boer Ahmad province, is close to the very ancient Iranian civilizations in southwestern Iran, the Alamite civilization, and they had a great connection during the 3rd, 2nd, and 1st millennium BC with the Elamite civilization. But the thing that is important, they are not civilizations, they are more small settlements. And there are 2 rivers, Beshar and Kherson, that they have been studied from 2013 onward to find different archaeological sites, and they found numerous archaeological sites that they are settlements or graveyards. And you can see here that Parsa Qasemi started doing a survey in this region, in the region of Beshar, Kherson basin, and he found more than 30 archaeological sites dated to the prehistoric period of Iran. And this survey was because of constructing a new dam, Kherson 3 dam, on the Kherson River. And this was the aim of this research, to find archaeological sites, excavate them, because after constructing the dam, all of them will be covered with water. So they started this survey, and they found more than 30 archaeological sites, and we select here 4 of them, Dehdumen, Monj, Dezak, and Lahsavare, that we could take samples from their copper-based materials, as we could analyze them, and you will see them 1, 2, 3, and 4 are numbered there. Dehdumen is a graveyard dated back to the 3rd and 2nd millennium BC. Monj is another graveyard, is a late Chalcolithic, late 4th millennium BC. Dezak is a small village dated to the 3rd millennium BC, and Lahsavare is another one, is a graveyard dated to the late 2nd and mainly 1st millennium BC, the Iron Age. And we selected these sites, and we selected different archaeological objects, and these are the archaeological sites and their excavation. You will see that Dehdumen and Lahsavare are graveyards, are very typical types of graveyards from the Bronze Age and Iron Age of Iran, but Dezak is a very specific, small settlement, a village that has been used, and they just found 2 archaeological copper-based objects in the site, but numerous archaeological copper-based artifacts from different archaeological sites. And these are the objects. You will see that they are from different types of objects, from the small dagger, vessels from Dehdumen, and different types of vessels, arrowheads, small decorative beads and bracelets and something like that. And one of the interesting things was that they could find also iron objects in the Iron Age 2-3 site of Lahsavare, but they couldn't find any iron object in the other ones, because iron started at the end of 2nd millennium BC, early 1st millennium BC in the Iranian plateau. So we firstly did chemical analysis using ICP, OES, and XRF, combination of them, and you can see here that most of the objects are made of tin bronze, and this is a typical graph for comparing tin and arsenic, and just some of them are made of arsenical copper, and it was very interesting. We just found arsenical copper in Monj, this black point, and also some objects from 3rd millennium BC from Dehdumen. And the rest of the objects are made of tin bronze with different tin content. And here is very clear, we can see that the late 3rd millennium BC and 1st millennium BC and 3rd millennium BC, we have arsenical copper, but after that we have just tin bronze. And also another one shows tin versus lead, and we see that there is no clear role of lead. Just we have one object here that it has more than 20% of lead, and I will show you this object. It's a very strange object, I will show you, but lead has no specific role. It's just impurity, maybe from the ore deposits, in fact, that they use. And the microstructure of objects was also interesting. These are two objects from Monge, the arsenical coppers, and we can see very specific microstructure. We call it superimposed structure. It means that they try to hammer these two very thin wall vessels, but they couldn't remove the whole of the primary coring, and this is why you can see this specific microstructure in this copper arsenic, low arsenic copper objects. But in the dead-human objects, we see more diverse techniques for shaping these objects, from casting here, this object, to hammering and annealing, and also the microstructure shows very small inclusions of copper sulfides and very small inclusions of lead, in fact, lead globules. And also this is the high lead axe that they found it in this shape. It's broken, 25% lead, and this is the microstructure of this object under SEM and also optical microscopy, and this object was broken after 3,000 years of burial in the grave. And it shows, I have no idea why they made this object. It's an imported object from another place or something like that. We are doing some lead isotope analysis to find some specific signatures for these objects, but they have not been done yet. And also for this object from the early 3rd millennium BC, there is a copper with low % of arsenic. We found that the size of the copper sulfide inclusions are larger than the other objects in this specific object that is made of copper. And while the others from the Detumen, from the last Avara Iron Age, they are very tiny, or very small size, but in this object they are very large. It shows maybe some different levels of smelting. Maybe they couldn't remove most of the copper sulfides and in fact make copper, metallic copper, when they wanted to make this object. And in the last hour, we also see specific types of hammering and annealing, but also we could find this specific structure that is superimposed again, because they are very small beads that they couldn't hammer them heavily, or maybe they couldn't, or they didn't need to anneal them in high temperature for a long time. But the microstructure is also very typical, and you will see that the size of the inclusions is smaller in general than the older object from the early 3rd millennium BC. But we could do some lead isotope analysis on some of the Detumen objects, and we could analyze 10 of them from the first season of the excavation, and we found that some of these objects have good correlation with Iranian copper ore deposits, but we had 3 outliers that they are here, they are very similar, and at the first it was a little bit strange for us, but after doing some comparison we could find that they have some correlation with copper ores and copper objects from Indus Valley. And it was very interesting for us, because we have in literature and the archaeological reports that there is a big relationship between Indus Valley here, in the border of India and Pakistan, and Mesopotamia here from sea route. Most of the archaeologists, they believe that. But we could find something here that is related to east of Iran in Indus Valley. And also there are some objects that their typology there are from here, Eastern Iran, from Shahdad, for example, that they have very interesting correlation based on their typology and shape with Indus Valley. But unfortunately, Shahdad has not been analyzed for provenance studies. Just some chemical analysis have been done on this very important site. So maybe it is possible that they, at the 3rd millennium BC, they didn't just use the sea route, but also they used some routes from the land, maybe from Indus Valley to eastern Iran and from eastern Iran to western Iran, but it needs more and more and more analysis. We are analyzing more, maybe more than 40 other objects from Dehtumen to find any relationship between western Iran and Indus Valley. And I know that because they have made of tin bronze, there are some problems for lead isotope analysis, but this was the only technique that we had to do some analysis to find some correlation between these areas, the 3rd millennium BC. As a summary, I can tell you that, in fact, in the late Chalcolithic and early Bronze Age, we have arsenical copper and tin bronze together, and also lead is impurity. We don't have any lead as a main alloying or addition to the objects, and also the sulfidic inclusions showed that the resources that they have been used are a mixture of oxidic and sulfidic copper ores. In the middle and late Bronze Age also we have tin bronze and arsenical copper to add, more tin bronze, less arsenical copper, because it's from the western Iran, and lead is another, again, an impurity, with just one case with high lead, that is a strange object, and also sulfidic inclusion. And during the Iron Age 2 and 3 in La Savare graveyard also we have tin bronze, and lead is again is impurity, and also sulfidic inclusions are similar. So it shows us a very similar process of metalworking, but just changing of alloying process from arsenical copper to tin bronze. And because mainly arsenical copper production has been an accidental alloying process in the Iranian plateau, it means that maybe they just changed their ore resources. Maybe they moved from the central Iranian ore resources that are high in arsenic to maybe more western Iranian or some other regions. We know that De Hossein has been used in western Iran, has been used for producing tin bronze in the Bronze Age and Iron Age. We have no idea about others. Somebody believed that maybe tin came from Anatolia or from Afghanistan, but based on the results from De Hossein, it means that maybe they used multiple resources from internal Iranian plateau and maybe also external part, and we could find some in fact, long distance trade during the 3rd millennium BC, but it's at the earliest stage we need to continue and develop results of analytical studies to find more accurate results. Thank you very much.
Any questions, please? First question, I'm just thinking about this question. In the cases of some relatively low tin content, how it can decide whether it came from intentionally alloying impurity or whether it came from intentional alloying purity or maybe some kind of recycling process?
Thank you. Thank you to come back here. Early examples of tin bronze, they have less than 10% of tin. But when you come to the 2nd millennium BC or even 1st millennium, you will see that some of them have 12 to 15, from 5 to 15. It's a wider range. So the thing, I think maybe the first time Niman Ezafati found this, that they use De Hossein, because De Hossein is a copper and tin ore deposit. It's not just copper or just tin. It's a mixture of copper and tin. It's cassiterite, copper and tin bearing ores. And maybe they use them at the first. And this is why most of these objects have lower tin percent. And after that, they learned that they can use tin as a separate material and add it to copper and in the middle of the 2nd millennium BC and later, and they can make objects made of tin bronze. Maybe the first step was just moving from an ore deposit to another one, and they maybe just found low tin bronzes. Yeah, maybe with some, I don't know that they had any idea about toxicity of this arsenic. Maybe they could live longer, and they said that maybe this is better to continue using this type. And recycling, of course, is a case. Always is the case. Yeah. But I'm not sure that at the beginning, maybe later, because in La Savoria, the range of tin is from 2% to about 18%. So it means maybe some of the objects that they have lower 10% they made by recycling.
I understand. Okay. Other question? Alice.
Yes, Omid, I have a question. I think I missed something, probably. Who said that in eastern Iran there was arsenical copper until the Iron Age?
No, in eastern Iran.
There is?
Yeah, arsenical copper.
Okay,
yeah.
And in that case, this arsenical copper is produced by using spice, I suppose.
We have two cases in Iran that they analyzed and found spice. One is in Arisman in central Iran.
Yes, I know.
Another one is in Tape-Hesar,
yes,
close to Damban.
Yeah.
Both of them are in central Iran. No evidence of using spice has been found in western Iran, in eastern Iran, sorry. And in eastern Iran, we have just one archaeological site that has been analyzed from the Iron Age and is Tape Yahya.
Yeah.
And just we have arsenical copper in. You know, the problem of Iranian plot in the first millennium BC in the Iron Age is that most of the settlements are in Zagros and in the highlands. We have less settlement in eastern Iran. And this is why we don't have any clear clear view about the eastern Iran in the first millennium BC. So we have just Tape Yahya, and in Tape Yahya we have copper and arsenical copper, but no evidence of spice. Could be, yeah. But these two cases of using a spice are from the late Chalcolithic period. Arisman and Tape-Hesar are older than first millennium BC.
Sure.
Other questions? Thank you again.
Thank you very much.
Let's go back to Europe, directly to Spain. Next paper, Early Middle Bronze Age stone molds in Central Iberia, 2 new flat X molds, Ignacio Montero Ruiz, Rafael Fort, Lorenzo Gardino, and Vicente Marcos Sanchez. Please.
Thank you, Bella. Good afternoon. So I'm going to speak about these stone molds, and the general question is to know where and when they start to use a real two-valve molds, okay? So in Iberia, we don't have stone molds during the Chalcolithic. It appears in the early Bronze Age, and we have mainly 2 big types. The upper one is a mold with the shape in the center of the stone, so this only works pouring the metal from the upper part. And a second type that's in the lower part of the image, when the shape of the axe is located in one of the border, mainly the butt, and this is the area where we cast the metal into the mold. But these molds have only one valve worked. The other is covered by a flat stone. Okay, it's better. But what happened is the option of 2 valves to do this plain access. Well, sorry, I am afraid that the type of the PowerPoint is completely different because all this moving, but doesn't matter. Well, last year appeared this object in Casa del Cerro de Perales in Madrid, close to the capital, and you can see the original position, and when they moved the upper stone, we saw the shape of a plain access. Okay, because we have the evidence of the cover by a plain stone. This is the picture of the both parts, And here, probably you have a recreation of the object. Well, new object, new technologies. Okay. It's nearly full, but it's just a little bit broken in this front part of the pouring area. Okay? But several years ago appeared a second mold that was also a plain axis and was broken in, I think it's, I don't know, well, in the butt is small, broken, and you can see the section that is heated and so on. We try to study these two molds to understand a little bit more about the technology and also about the stones, where petrographic analysis only could be done in the Cerro de Perales and showed the presence of quartz, feldspats, and muscovite, and so on. But the diffraction, the X-ray diffraction, let us identify more precisely the type of stone. The sample from Cerro Perales is subarcose with a high amount of potassic feldspar, muscovite, and some calcite. And the second one, the La Serna, is a completely different, so the composition and the type of stone is not the same. Both are sandstone, but different types, and are more pure quartz and don't contain feldspars. Well, this is the geologic map of the Madrid region. So we are located in this area that's more mainly tertiary, and this is a detail with the location of both sites, the Casa de Perales and La Serna. Both sites are only 15 kilometers far, so, but they are located in these Miocene terrains, and according with Raphael Ford, that is the geologist involved in this research, the type of stone could come from numbers 20 and 17. So they are very close to both sides, so there's no looking for special or long distance stones, so are locally produced, but in each case from different type of sandstone. We did X-ray fluorescence to know more details, and we found that both types of stone are different, and the composition of bismuth, manganese, or magnesium are different in both. We are sure that the two parts of the mold are from the same type of stone, but what's more interesting for me is that we can detect some tin, lead, and copper. You can see the point or not? No, well, but it's marked in the picture. So in both molds, so that means that a copper, tin, bronze will be involved in the casting of these objects. It's important because we are now moving in this bronze alloy, and the question now is, we have the molds with the plain cover, and they produce bronze. Okay. 2 years ago, Perez, Rich, and Soriano published a new classification of the axes, including the molds. For example, we've found that the mold from La Serna that was published is classified in this TRA, TM, SB, CC category. Don't try to understand the names, but with a similar group of axes from different parts of Iberia. So the second, the new one, the Casa Perales, could be classified in the in this one. I destroy. You can put it. Sorry. No worries. Now we have to restart? Yes, of course. Okay. So I can explain things meantime. So we have two different types because one axis is longer than other and have different shape. And we try to detect some objects of these types showing the typical shape that show that you have a two-bulb, okay, even the microphone, two-bulb C. And in the picture, if we can see later, we find that the same types of the molds, we detect some of these bivalve axes produced with this kind of not only with the plain cover, all right? And we are moving just in the middle of the second millennium BC. It seems that that's the moment when the tin bronze also appeared in these parts of Iberia. And what we are sure is that in the previous moment, in the early Bronze Age, we don't have any evidence in the molds or in the axes of this use of two-bulb molds. Okay. Yeah. Okay, we move quickly. All right, so we were here, then move again. Okay, those two different types, and you see the line is around the middle of the second millennium, but you can see the abyss axis fixed, the Pontevedra fixed with the La Serna type, and the abyss with the Casa Perales. But you can see in the draw, they're clear manufactured by two bulbs in this. But, for example, all the axes and the molds from the Largar that is located in this our part is a little bit earlier. We have no evidence of this type of two-bulb mold. But the last, you can see this type from Bujoes Barceló, that we have the two bulbs, and also it's necessary to have some holes or some element to fix both sides. In the other, we see only plain surface. There are no evidence that they join two bulbs, okay? So the question or the conclusion is that we are using local material, we are producing the first copper tin alloy, and it seems that it's the moment that we are changing to one type of mold to the other. But these two bulbs are located mainly in the Atlantic area of the Iberian Peninsula, all right? Well, Madrid is in central, so we are connected with this Atlantic area. And later, in the late Bronze Age, we have many evidence of access with this two-bulb use, and even started the metallic molds in this late Bronze Age moment. So there's a change of this. And now my last question is, what is happening exactly in other parts of Western Europe when they start to use these bivalve, real bivalve molds? Okay? Thank you very much. On time even with the, in the interruption. Okay.
Question, please. Yes. Microphone. Yes.
Well, Ignacio, the Iceman X, 3200 before Christ, was certainly a bivalve mold because it's not been hammered and it's perfectly symmetrical. So that is quite clear.
Okay, well, this, I suppose that because I know there are some early Bronze Age axes in Germany and France, so that means that Iberia is slightly different technologically at this bronze moment. This is what I'm trying to go. Thank you.
I'm thinking about that it would be interesting to take some reconstructional experiments about simulation of the casting. Because why does it change this process, the covering, and which affected in the surface of the alloy?
Well, I can imagine that there are some effects. We can detect some in the section of the axis, because when one side is plain, you have more difficult to have a symmetric structure. But about the cooling and the question, I don't know exactly, because they are using, in this case, stones. We are working with more frequently are sandstones that are good.
Cooling, I don't think about because it's a closed area.
I know, but the pouring system is the same. You have to pour vertical, the lower inclination, and pour inside. The difference is that you have two symmetric parts of the
yes,
object.
it's other since the forming, the shaping. It's a different process. The next. Okay. Yes?
Thank you very much. Such an interesting talk. I have a question. Is it the stone molds were like overwhelmingly used for casting, or also the clay molds were used at that time as well?
I'm not sure I understand.
Whether the clay molds were also used during this time for casting, or mainly the stone molds?
Well, we have evidence of the stone because we appear in the archaeological record. We are not sure. Only in the late Bronze Age we detect clay molds, metallic molds, but nor in Chalcolithic and in early and Middle Bronze Age we don't have any evidence of clay molds.
Thank you very much.
Okay, thank you.
Last but not least, coming home to Crete, a late preparation family in death, Archaeometry of grave goods from the Petras necropolis in the eastern Crete. Speakers Susan Ferenc, co-authors Alessandra Giumlia-Mir, Philip Betancourt, James Mully, Metaxia Tsipopoulou, Aurora Arshous, and Sotiria Kiorpe.
Hello, everyone. I just would like to preface this lecture by saying that the next few lectures use the same XRF methodology that I briefly mentioned here, and then we don't really talk about it so much in the next few lectures in terms of the methodology. And so we are a big team effort on our projects, and we're all very glad to be here and to see everyone here today. So. The Minoan palatial site of Patras is located in eastern Crete, and its excavation has been under the direction of Metaxia Tsipopoulou since 1985. In addition to the palace on Hill 1, a pre- and proto-palatial necropolis is located on Hill 2, along with settlement remains from the final Neolithic period, meaning as early as around 3500 BCE, and also the late Minoan III period, around about 1400 to 1100 BCE. The necropolis consists of many house tombs and other types of burial structures, dating to all phases from early Minoan 1B through middle Minoan 2B, meaning about 2900 to 1750 BCE. The Elite House Tomb 2, dating to middle Minoan 1B to 2B, around 1950 to 1750 BCE, was founded on top of earlier stratified remains, including burial structures 23 and 28, dating to middle Minoan 1A, meaning about 2000 to 1950 BCE. Burial structure 28 was excavated by Aurora Alshaus and Soteria Chiorpi. A primary burial of a man was found along with a disturbed primary burial of a woman and the secondary burials of 2 children. The metal jewelry includes decorated gold, spool-shaped, and other types of beads. Further, a dagger made of arsenical copper with a bone handle and silver-capped rivets also came from the burials. The results of the microscopic and XRF analyses will be discussed, and they help to elucidate and differentiate the metallurgical technologies that were in use. Each of the metal artifacts was analyzed with the non-destructive technique of X-ray fluorescence spectrometry in order to determine the elemental content of the metals and alloys that were used to make the objects. The XRF system is transportable as several parts to be assembled on site. It was brought to the INSTAP Study Center for East Crete, and with the appropriate permissions from the Hellenic Ministry of Culture, the artifacts were analyzed by Alessandra Jumlia Meyer. Each item is first examined with a digital microscope to identify ancient manufacturing techniques and to locate clean areas on the corroded objects, such as those made of silver or copper alloys, where the XRF would be able to give the best results. The XRF system is calibrated with metal standards made of alloys in certain percentages that are known from antiquity. Their use for calibration ensures accurate results of the percentages of elements used to create the ancient artifacts. Burial structure 28 was a pit dug into bedrock, and it contained the primary burial of an adult male who owned the copper alloy dagger. He was positioned with his hands near his shoulders, and the dagger was found on his left rib cage. The hands-on-chest gesture is usually found on Minoan male figurines from peak sanctuaries that are also often depicted with daggers belted at their waists. The complete blade of the dagger includes 4 rivets in situ. The XRF analyses show that arsenical copper with 1.5% arsenic was used to cast the blade with a midrib. It is Keith Brannigan's type 5A, and parallels from the tholos at Platnos in the Mesera are broadly dated to early Minoan 3 to middle Minoan 2. The dagger was hafted into a handle that had a bone spherical pommel on the end, remnants of which were extant in the burial. 4 rivets are still in situ, and there are 2 additional rivet holes at the heel end. 2 of the rivets are shorter, and they still hold pieces of organic material in the corrosion products, perhaps remnants of a wooden handle that was finished with the bone pommel. 2 longer rivets also held the handle in place. The XRF results show up to 2.3% silver on the rivet heads, meaning they once shone with a bright silvery surface. They were capped with silver foil that was then adhered to the rivet heads with diffusion bonding using copper salts. We have other examples of silver-capped rivets from Minoan Crete. A pattern of corrosion on the blade is perpendicular to the length of the blade and suggests the shape of one edge of an unpreserved scabbard. Also excavated in burial structure 28 immediately north of the man with the dagger, was a primary burial of a woman with evidence of secondary manipulation, namely retention and rearrangement of skeletal elements into a pile. Also in the same area with her were secondary skeletal remains of an infant and child who were previously interred there. The woman wore the gold jewelry and also other types of adornments. 3 of the gold pieces are spool-shaped beads with incised decorations of swirl and wave patterns in combination with net and floral motifs. This shape and type of decorated bead is well known from the Minoan house tombs of Moklos. Their well-made, hollow construction was accomplished by cutting rectangular strips with holes and circular discs from sheet metal, bending the strip into the circular band and attaching the discs to the top and bottom of the band. Several different spots on the beads were analyzed, and the results indicate that all parts of each bead were produced with gold sheet from the same batch of metal. The results also show that the metal used was very good quality gold with a low silver content. The silver content originally may have been somewhat higher, but the intensive hammering and annealing during the production of the gold sheet and the very long time of burial in the soil probably caused some of the silver and possibly also some of the copper to leach out of the metal. Several analyses of different locations on the sides and rims of the middle spool bead shown here, and especially at the joins of the parts, demonstrated that the solder used for attaching the parts of the bead to each other was a gold alloy with 19% silver and traces of copper. The copper may have been higher originally, and it has corroded away over time. 2 spherical gold amulets were also found among the jewels of the woman's burial. They are fairly large at 1.5 centimeters in diameter and quite heavy. In comparison, the gold spool beads are only a couple of millimeters smaller in diameter, but weigh 1/3 of the weight of the spheres. These amulets are not made simply of sheet metal like the spool beads, which are a typical Minoan style of jewelry. The 2 spheres are cast gold with 2.5% silver, the latter of which originally may have been higher. They were then finished by polishing. The example on the right has numerous platinum group inclusions at the top, which hindered the polishing and caused the scratched surface. The amulets also may have been used as containers for herbs or other materials with magic meaning. We have not found a parallel for this shape of amulet in Minoan Crete, and the casting technology with a generous amount of gold suggests the possibility that they were imports to the island, probably from farther east. Other eastern imports of fine jewelry have been identified among the finds from the Patras necropolis. A unique gold item among the gold jewelry is a composite bead made of a faience cylinder and a complex quadrispiral attachment made in gold. Even though the cylinder looks white now, it originally had been a pleasing blue color due to the copper used as the colorant in the faience recipe. This is an example of faience being used to imitate the semi-precious stone lapis lazuli, which was a coveted material of Mesopotamian royalty that was traded from the area of Afghanistan where huge quarries are known. The faience cylinder was mounted with gold perforated discs on its ends, and they in turn extend on 2 sides with double spirals. Under 50 times microscopy, clear evidence for solder is visible on the spirals. The entire apparatus started as one piece of gold that was flattened and perforated in the areas of the top and bottom of the cylinder, and the rest was hammered, elongated, twisted into wire, and then coiled into shape. The helicoidal seams along the wire are visible under microscopy, and they are remnants of the manufacturing process. The coil was flattened, and solder was applied to the coils to keep the shape. The gold is good quality with up to 1.3% silver, and copper is present in the solder. Another unique item in the Patras necropolis is a duck-shaped pendant figurine, carved out of rock crystal and adorned with gold leaf. The duck was provided with incisions to form a beak and wings and a hole in the tail for suspension as a pendant. The hole was covered by the gold leaf, which also bound the wings to the body. The pendant was turned into a figurine with the application of the gold, and the duck is symbolically prevented from flying away. Visual inspection under microscopy determined that the leaf is one piece. The XRF results show very pure gold, as expected, because it is so thin at less than 1/10 of a millimeter. The rest of the gold jewelry from the woman's burial in structure 28 is comprised of several pieces of strips and foil and very small beads of various shapes, like cylinders, plain and ridged globules, an incised beryl, a four-pointed star, a multitude of tiny cast rings, a minuscule, intricately coiled bead, and many more. They exemplify the wide range of manufacturing techniques such as casting, hammering, incising, repoussage, and filigree. Burial structure 28 is only one example among many rich contexts in the Patras necropolis, which has yielded hundreds of gold items. And I haven't even mentioned all the silver pieces. The amount of silver jewelry from Minoan Crete has greatly increased due to the excavation of this one necropolis. The analyses of the gold objects have yielded important conclusions. The metal was probably natural gold containing silver, to which copper was added in some cases to lower the melting point, except for the objects where it was used as a solder. The two heaviest cast gold objects containing the PGE inclusions, which might be an indication for the provenance of the two spherical amulets. For example, PGE inclusions are well known from Egyptian gold jewelry. We must note, however, that PGE inclusions are found elsewhere as well, for example, the gold from the Pactolus River in Anatolia. The gold found at Patras is certainly not from Crete. It was imported as raw material and then sparingly used in manufacturing sheet, foil, leaf, and wire. The spherical amulets stand out among all the Patras gold pieces as being heavy cast objects. This stratified pre-palatial Middle Minoan 1A burial context sheds much needed light on the dating of similar metal jewelry found in other widely dated communal burial contexts elsewhere in Crete, such as the house tombs of Moklos and the tholos tombs of the Mesera. Thank you.
Any question?
A small question. How these gold beads were used? The smallest one, how they were used? How did you find it in situ?
Oops, wait.
Yes, these ones.
The ones at the lower right, they are probably the tiniest, I
Yes.
think. They're about 2 millimeters in diameter, 1.5 to 2 millimeters. And our co-author, Ria Chiorpi, was the physical anthropologist who excavated the context, and she noted that they were around the head of the woman. And it's possible that they were used perhaps in a hairnet or somehow decorating a headpiece of some sort. We don't know exactly.
Thank you very much.
Thank you very much for the fascinating presentation. So I may have missed the part, but regarding the jewelry, you mentioned that there's a fine gold wire formed into a spiral shape, and you mentioned that a solder was used. So I'm wondering what kind of solder is used for?
Here.
Yeah. Yes.
We think it was added to the coil just to help keep it flat, actually.
So it's not metal.
It is a solder, yes. The wire was coiled, and then they didn't want it to move, so they put solder on top of it. And there are parallels in different pieces of jewelry from Ur. From Ur in Mesopotamia. So it's, yeah. Gold and copper and silver. Yeah. Same, yeah. Yes, I would like to add that Metaxia found all this stuff because she had people doing all the time, from the beginning of the excavation, water sieving. It would not have been possible to find these tiny pieces without water sieving of the entire soil of the excavation.
Mm-hmm.
As I see, this gold, it's very pure raw material, as I see. And looking the inclusions from the platina groups in the surfaces, it's the physical inclusions. Is it indicated that it's a direct process, not remalted, just directly malted, not recycled, not remalted, because it's physical inclusions.
Use the microphone.
Pardon?
I'm just saying you can remelt it and you still have the inclusions inside. No, it's not. It's not. These are PGE inclusions which are found in gold in quite a few deposits. And they are, we believe this comes from Egypt because we have in Crete several, the narrow, very close connections to Egypt. And in Egypt, the gold from Nubia has these kind of inclusions. So if you cast it and you remelt it, you still have the inclusions inside. They go to the bottom of the crucible. One point is, you see, this is one on the right, is probably the last casting, because it has more inclusions, and the other one almost has none, just one, yeah. So it means that most probably the inclusions were at the bottom of the crucible.
That's what I mean.
Yeah.
Okay, thank you. Question? Thank you again, Susan.
Thank you.
So I would like to thank again all the 4 speakers for this session. Session is ended. Afternoon coffee breaks begin with posters, and the next session will begin 4:10 p.m. Thank you.
Okay.
I just wanted to see the slides, just because of the size, and sometimes they change.
Yes.
I sent it to Susan by email. Yeah, is that? Will that fit in the thing? Yeah, that's perfect.
come up. Great. Just what I want to check. Great. And do you have? I'm not going to point at it, but that's okay.
I make a presentation tomorrow. Do you think I can use my PC?
No,
Because
it's not
I
possible.
I will use my CT data. It's so heavy.
Okay.
Ah, okay, yes. But I closed it again. Please take your seat. Take your seat. We are running late. So, yes. Okay, so we start with a paper by Γιώργος Δεθυμιωτάκης, Alessandra Mzumlia-Meyer, and Susan Ferenc. Susan Ferenc is going to read, and the subject is the complex metallurgy of the Minoan ring from Castelli Pediada.
So I'll do the introduction, and then Alessandra will come up in a couple minutes and do most of the, we will tag team.
Okay.
The signet ring presented here belongs to the small group of rings with circular bezels, most of them dating to the Middle Minoan III period, about 1700 to 1600 BCE.
It is significant for two reasons. The first reason is relevant to the complex and skillful manufacturing techniques of its construction, and the second reason refers to the number and nature of the metals employed, among which iron stands out for its rarity in Minoan metalwork. The ring was found during a rescue excavation by the Ephorate in the Kambatakis plot at Castelli Pediada, where a large proto- and neo-palatial settlement with a central palatial building has been under excavation since the 1980s. The ring was excavated on the floor of a room within a large neo-palatial building, MM3 to LM1A, which spans the area of the excavated plot and then some. In all likelihood, it was an extensive architectural compound, but its borders cannot be traced due to the limitations of the present evidence. The pottery included many large and small chalices and large stands with relief decoration, all of which indicated communal feasting activities. The Castelli ring is poorly preserved, with its surface and core full of cracks, splits, and corrosion. Because of this reason, the inner construction has come to light, revealing important manufacturing details. Specifically, to help us understand its ways of manufacture, the side views of the bezel, which we can observe in these high-resolution photos by Jeff Vanderpool presented today, show the layers of metals. The seal surface, in particular, is made of iron, an extremely rare metal in Minoan metallurgy, specifically when it comes to Minoan rings. There's only one other case of a polymetallic ring with an iron bezel surface, which is the well-known example that was worn by the priest on his little finger when performing the renowned human sacrifice at Archanes Animospelia, dated to Middle Minoan 2b to 3a, about 1800 to 1650 BCE. The Animospelia ring is iron on silver and corroded. We use the term polymetallic because the solid bezel of the Castelli ring is composed of 4 layers of metals. From top to bottom, they are the following: iron inlaid on the arsenical copper bezel surface, then a layer of a whitish material, and a metal sheet on the lowest surface that touches the finger. 2 silver rivets were used to help keep the iron in place. The edges of the copper-based bezel were bent over and around the edges of the core whitish metal and the lowest sheet underneath to keep it in place. This technique came to fruition in the construction of later gold signet rings like the Sacred Mansion ring from Poros. The hoop seems to consist of 2 strips held together by crimping the outer one onto the inner one, which is the same technique used on the bezel. The outer surface of the hoop has parallel incised lines across it, as on most Minoan rings, though here they are rendered in a more modest way compared to the later fine neopalatial gold rings. An example of unusual decoration preserved on one side of the Castelli ring appears for the first time. It consists of a row of minute circles, each with a dot in the center, 8 or 9 across the width of the hoop near the bezel. They were probably made on the wax model that was used for casting the bezel and the hoop together. Such circles with a dot in the center is a very popular motif in the old palace glyptic, and this is obviously the source that the ring makers used. The representation engraved on the bezel belongs to the array of unending rapport compositions. It is a quatrefoil net arranged in 3 rows, all with a central dot among petals. They all share the inner petals, thus creating the impression of a net. We believe this was done on purpose to include as many quatrefoils as possible in the extremely limited iconographic field, and altogether it creates the impression of a graphic composition. The quatrefoil net, though rare, is not totally absent from the repertory of pre-palatial seals. It appears twice in the sealing surface of 2 ivory seals from the Tholos tombs at Ayatriata and Platanos. A third pre-palatial example, this time made of hippopotamus ivory, comes from Schinocapsula near Cittia. It seems to be a predominant decorative element among many others engraved on seals of this period that combine rectilinear and curvilinear motifs. It disappeared as a sealing motif in the Old Palace period and then re-emerged in the Neopalatial period as demonstrated by the discovery of the Castelli ring, which probably provided a new meaning for the decorative motif compared to its previous incarnation. As will be further indicated in the following part of this technical analysis, the ring is an exceptional work of art and technique made by skillful artisans and master metalsmiths active in a palatial workshop, possibly in the Canossian environment. And now Alessandra will take over from here.
So we did XRF, of course. We couldn't do any kind of other analysis because we couldn't take the ring out of to a lab, for example, to be looked at the scanning electron microscope. So we had no other chance. As you can see from the slide, the bezel and the hoop are very similar. So they have been cast together. They contain 5% of arsenic and 3% of tin, and so on. The back of the bezel is a similar, has a similar composition, but it is not exactly the same. There is some lead coming from the core. The whitish core, which Susan showed just before, it is lead, simply lead. There is some copper and iron which come from corrosion of the other parts. The 2 rivets are made of silver, of course with some contamination of copper and iron, again from the other parts. One of the rivets has much less iron and copper, which of course confirms the hypothesis that they only come from the environment. There is no copper in the silver. Yeah, the inlay. The inlay is iron, and it contains 7% of nickel, and there are also traces of cobalt. So we are convinced that the inlays are made of meteoritic iron. The rivets consist of two small pieces of silver sheet rolled up to form a tiny, tiny tube, which was employed as a rivet. It was then hammered into the surface. The hammered sheet is harder than a cast rivet made of silver, of course. We have other examples of these in Crete. There are other rings with silver rivets, for example, a ring from Mochlos, and also that one has these, I call them rivets because I don't know what to call them in a different way, are made of rolled up silver sheet. So as I said, the core consists of lead, and now it is extremely corroded. It would be good to take it out, actually, because it disturbs the conservation of the entire piece. This technique of having a core made of lead is well known in Crete. There are several other examples of these basals filled up with lead. The back of the basal is, as I said, is also made of arsenical copper, and it was applied after the lead core was inserted, so it closes the basal, so to say. And it was kept in place by crimping it on the edge of the basal. Let me see if I can show you these. This is the crimping. You can see the fold here, I hope. So these rivets do not completely pierce the basal. Only one of them is visible at the back. The other side, you see the flat underside of the ring. You cannot see any traces of the second basal, the rivet, of course. So about iron. In this period, and we are talking about the 17th, 16th century BC, iron is very rare in Greece and in general around Europe and the Mediterranean. And the known iron examples we know of consist of meteoritic iron. What I'm showing you here, the one on the top, is one of the famous beads from Gerze in Egypt. There are 5 such beads found together, of course. They are made of meteoritic iron, and this is the earliest piece I know of. The other example I'm showing you here is this dagger from Alacha Höyük, which has a hilt made of gold, and it is dated mid-3rd millennium BC. It is now in the Ankara Museum. The most famous object made of meteoritic iron is the dagger of Tutankhamun, dated about 1334, 1325 BC. It has been analyzed by XRF, and the iron contains 11% of nickel and 0.6 of cobalt. So it shows quite clearly that at the time iron was more precious than gold. What I'm showing you now is an ethnographic example. It is an Inuit harpoon made of narwhal tooth, yes, and meteoritic iron. Normally, it is thought that early iron objects which contain nickel are meteoritic iron. However, yes, these are examples of meteoritic iron, meteorites, and with a characteristic Wittmann-Steffen structure. The nickel is in these formations inside the iron. Some excavation at Kale-Höyük in Anatolia, led by the Japanese Institute of Anatolian Archaeology, have found that several objects made of iron found there contain nickel. However, they also contain some slag, and slag is a certain indication of smelted iron. So we are to be perfectly sure that we are dealing with meteoritic iron, we need destructive metallography or something like this, but we cannot do this with this ring. But nevertheless, I believe that in this case, we can safely say that this iron was considered a special material because it is on this representative object, and it also has the silver rivets. Yes, I want to add that the Egyptian name of iron is Bia en Pet, the metal from the sky. The Sumerian names of iron, one of the Sumerian names of iron, they distinguish different kinds of iron, is Anbar Nepisaz, the iron from the sky. And some Hittite texts also describe the sky as being made of iron because there were all these iron meteorites coming down. So the idea that iron is a divine material is quite clear. It was widely diffused. So as you have seen, the Castelli ring has a complex structure. We have a copper-based alloy containing arsenic and tin. It had a rather golden color. The core was made of lead. There are two decorative silver rivets and this meteoritic iron inlay. It is quite difficult to work meteoritic iron, so this artisan must have been quite skillful. And this ring must have been considered as an especially precious and powerful amulet. Thank you very much.
I'm sorry, I don't think we have time for questions because we're already late. So we can proceed to the next paper. You think we have time? It's 25 already. Okay, so the next one is copper alloy kouros recovered by the Greek police on Crete in 2015 by Christos Sofianou, Philip Betancourt, Thomas Brogan, here present, and again Alessandra Zumlia-Mayer and Cleo Zervaki.
All right.
Dr. Brogan.
So you just hit the arrow to advance the slide?
Big arrow.
Big arrow in the middle. Okay. So I think on behalf of our team, I too want to thank the organizers, some of whom are on the paper, and Ellen and the Ephorate for hosting us. This is just a fantastic venue. So I've been asked to read the paper because I can read the English faster than everyone else on the team. Others have written much more of this paper. I'm a reader today.
Bravo, Pedro.
So our paper today is the first part of a planned two-phase study of a fascinating and unique Minoan object recovered by the Greek police on the 28th of May 2015. Today we present the discovery, conservation, and analysis which has confirmed the object's authenticity. In a subsequent publication, we will devote more attention to its place in Minoan studies. So the recovery by Christos Sofianou. Late on the 28th of May 2015, Christos Sofianou received a call from the chief of the Lassithi Police Department, Yorgos Paniotakis, asking for her help to determine the authenticity of an ancient artifact. As he explained, the object in question had been recovered during the arrest of 3 men in Satia involved in trafficking antiquities. Chris assumed it would be something simple like pottery sherds or a broken vessel, as is usual in such cases. A little while later, in the office of the police chief, she was surprised to see a large group of men who were fully armed and dressed in black, straight from the operation. One of the officers presented a box which the chief promptly opened. Far from the expected sherds, the box contained this magnificent large bronze male figurine with gold attachments. Seeing the surprise on her face, the officers asked immediately if the object was real. From the size, condition, stance, and hairstyle, she said that it probably was a genuine Minoan artifact, However, the final decision would be made by a committee of experts. The figurine was recovered as part of a lengthy operation by the police department of Ios Nikolos in cooperation with the special counterterrorism and organized crime departments in Heraklion. The police team in the room consisted of the agents who had coordinated the seizure of the bronze statuette, which was soon transferred to the conservation department of the Ios Nikolos Museum. An expert committee was later organized by the Ministry of Culture, including Yorgo Thimiotaki, who's with us today, and the then director of the Heraklion Museum, Stella Mandalaki, and Krisa Sofianou. On the basis of its morphology and style, the committee determined that it was a genuine Minoan figurine dated to the Neopalatial period, so 1700 to 1450 BC. They were less sure of the gold, but noted that it was the largest bronze Minoan figurine ever found, and thus should be valued at 1,300,000 euros. Where Themiotakis later noted his surprise that the men arrested did not claim it was a fake, which would have lowered the severity of the charges against them. So on to conservation. So the bronze statuette, AMS 14423, measures 28 centimeters tall and weighs 1.5 kilograms. It's almost intact, with the exception of an area beneath the base, possibly where it was anchored or mounted, and the tip of the right hand. The morphological features of the statuette, as well as the nature of the corrosion, attest to its authenticity, fully consistent with the judgment of the specialized committee that examined it. Condition, pathology, and description. The conservation condition is poor but stable, an assessment supported by long-term monitoring of corrosion development. From detailed macroscopic and microscopic examination, the statuette displays a relatively uniform surface with advanced corrosion. In some areas, the bronze is almost completely mineralized, while only a few zones show active corrosion. The statuette retains its overall form and many anatomical details, but its original outer metallic surface can no longer be located. The corrosion derives from a combination of factors whose precise contributions cannot now be determined, since the conditions of the burial environment, for example, the pH of the surrounding conductive solution, fluctuations in that environment, the presence of oxygen, and chloride-bearing solutions, etc., are unknown. Now, the patina is a thick, coarse, and green in color Robiola type 2. It is also not homogeneous, as some protuberances of corrosion have become detached. It also appears that the looters attempted to clean the object, which damaged parts of the surface. Some deformation corrosion was likely caused by localized galvanic effects, while longitudinal cracks in other areas may stem from thermal fluctuations. This phenomenon is notably more intense on the left side of the statuette, suggesting a localized microclimate that accelerated corrosion. Cracks elsewhere in the body may be attributed to casting defects, such as rapid shrinkage of molten metal and the resulting internal stresses. Throughout the object, the typical chemical and electrochemical corrosion is observed, is that which is observed in prehistoric cast objects from copper alloys, with corrosion products occurring in the proper sequence and relation. So you have a layer of cuprite as formed as a thick, compact layer in direct contact with the original metal substrate, visible beneath the green patina. On the front side, microscopic analysis revealed tenorite beneath the green corrosion surface. Over the entire surface, there is also a friable layer of malachite, which is a sign of its burial in soil and often occurs in the form of nodules that are visible over the entire surface. Due to the corrosion progression and perhaps previous cleaning attempts, many of the nodules have lost their original green surface and now expose lower layers of cuprite in red-purple tones. Atacamite, I'm not sure I'm going to pronounce this correctly, atacamite and paratacamite appear in severely corroded zones such as the face and left arm. So pre-cleaning analyses. Before beginning conservation, Alessandra Jumlia-Mayer conducted XRF analysis on 10 spots to determine the composition of the copper alloy and the gold foils, which were then compared to published ancient benchmarks to confirm material authenticity. In both cases, the composition were consistent with known Minoan alloys. Following verification, Cleo Zervaki began conservation, and continues her report. Removal of the gold foils. Microscopic and macroscopic analysis initially revealed traces of adhesives around certain gold foil, most notably on the right side of the boot, on the back near the belt and on the legs. It was clear that the foil additions were not original, but most likely added by the looters to increase the value of the object. This conclusion was reinforced by the presence of modern adhesives around the foil. In genuine ancient applications, the gold would have been wrapped or burnished, and any organic adhesive would have long since degraded. The foil on the legs above the feet appears to have been affixed in locations where evidently there was no original gold. Also, their contact seems better than that of the foils on the boots, groin, and belt. The decision to remove them was deemed necessary both to enhance the objects, to confirm the object's authenticity and to facilitate proper conservation. They were labeled A through G in locations from the locations from which they were removed and recorded. Now, after trials with various solvents, acetone was chosen to soften the modern adhesive. Upon removal, it was confirmed that the foils had been applied over a deposit of burial sediment lying on the surface corrosion of the malachite. This sediment would not have existed had the foils been present in situ during the burial period. Under foil G, there's a large area of damage in the patina, revealing a sizable region of cuprite and patches of lighter green new patina. With the cuprite corrosion, there was also parallel tool marks that were clearly modern. It's even possible that the foil was applied specifically to conceal the damage that occurred from the early cleaning by the looters. Now, a spot test for nitrocellulose adhesive was performed on the adhesive itself, applying half a gram of diphenylamine in a 90% aqueous sulfuric acid solution. The appearance of a blue-violet coloration, which you see here, indicates the presence of nitrocellulose. Had the color remained unchanged or turned yellow, orange, green, or brown, it would signify its absence. It's worth noting that nitrocellulose-based adhesives are among the most common adhesives used in the conservation of archaeological artifacts. So cleaning. Mechanical cleaning was performed under a Leica M60 stereo microscope at 10 times magnification. A sufficient sample of soil deposit was retained for future study, and no cleaning was performed on the base of the statuette, leaving it untouched for future analyses. Adhering deposits were removed using metal or wooden microscalpels, depending on the crust thickness, and where necessary, softened by applying ethanol with a brush. Throughout the process, contact with the object was made using gloves. And in the final stage of cleaning, residual loose soil was removed using a soft bristle brush mounted on a rotating metal shaft, a sheepskin wheel. And the object is stored in an airtight container with silica gel. Photographic documentation followed using a Nikon D610 with a Sigma 105mm 1.1 by 2.8 macro lens, and via the Leica M60 stereo microscope with an MC120 HD camera at various magnifications. It should be noted that no stabilization or protective coating has been applied to the surface so far, because the object's shown absolute stability during its storage over the past 10 years. Such protective interventions may, however, eventually be necessary if it is transported or displayed in a more demanding environment. However, these protective treatments can alter the object's appearance. So now we move to analysis of the Kouros by Alessandria Jumna-Meyer. The statuette was first examined in 2015 and in the state in which it had been recovered. This was done under a digital microscope with analysis by XRF. Microscopy revealed a thick, compact layer of cuprite beneath a rather friable malachite layer. In the most corroded areas, such as the face and base, active corrosion was visible. Traces of modern glue were evident in the area around the gold foil. The general appearance of the patina was consistent with that expected of ancient bronzes and comparable objects excavated on Crete. Following the complete cleaning of the statuette in 2023, a second series of non-destructive XRF measurements were carried out on various body parts. These results were compared with the measurements taken before conservation on the uncleaned surface. Hard corrosion warts are still present, covered by rough, thick green patina. Corrosion crackling is widespread, especially on the arms and legs near the elbows. The The cuprite layer beneath the malachite patina is exposed in areas where the largest corrosion nodules had likely been removed by the looters. Some of the alloy's original elements have leached out, which is reflected in the irregular analytical results. Calcareous soil material is firmly embedded also in the patina. The tin, arsenic, lead, and antimony contents in the surface layers are certainly lower than that at the time of production. Cuprite, the first alteration product of copper in its alloys in oxidizing environments, also tends to redeposit on the surface, often producing higher apparent copper readings than the metal bulk. The aspect of the patina suggests that the statuette was exposed to cyclical corrosion processes with alternating humid and dry phases that promoted the alteration and heavy corrosion of the metal. Under such conditions, tin in the alloy can also redeposit on the surface after leaching out of the metal graphic structure. So patina samples collected during cleaning were analyzed by XRD. In addition to cuprite, they revealed copper chloride hydroxide hydrate alteration products, calcium carbonate and silicon oxide, as well as a lighter phase rich in tin oxide, indicating redeposition. The stratified corrosion layers with their hard protruding warts and pronounced corrosion crackling cannot be artificially produced except with highly specialized and costly equipment not normally available to the general public. The original composition of the statuette must have been copper with approximately 5 to 7% tin and at least about 1% arsenic, with very low levels of lead, antimony, and possibly some nickel. Its composition is comparable to that of other Minoan figurines, which typically contain both tin and arsenic with only trace amounts of lead. The results can also be compared with analyses of objects from Habuba Kabira in Mumbakat, which show a similar tin-arsenic pattern. Craddock's analysis of 6 Cretan Middle Bronze Age figurines of unknown provenience or date revealed irregular compositions with tin contents ranging from 0 to 1.9% and low arsenic levels of 0.2 to 0.3%, with an average of 5 to 6% in 13 examples. 3 are made of arsenical copper, 1 to 1.6% arsenic, but most have variable and erratic tin contents and low arsenic, closely comparable to this kouros. So, conclusion. Trafficked artifacts bring a host of problems to those tasked with their conservation and study. When found, many scholars assumed this figurine was a fake because of its close resemblance to the ivory figurine from Building 5 at Palekastro, the so-called PK kouros. You see it on the right. For this reason, we thought it was important to stress the careful steps that have been taken by the committee, the conservators, and the archaeologists to determine its authenticity. Because of time constraints, we'll end with just a brief comment on style, date, and possible context. The figurine stands upright with its feet close together, its arms outstretched with both hands pulled back against the chest, and you saw some clay, similar versions in clay in a presentation by Susan Ferentz a little bit earlier. The artist paid careful attention to the hair, which is rendered in 5 round tresses, 3 beginning over the forehead, which fall in S-shaped curves down the back, and 2 more, one on either side, which wrap behind the ears and fall as snaky singlets over the chest and down to the waist. The figure wears a single band over the forehead and a thick belt or zoma around the waist with a codpiece on the front and a front and back flap. He stands on a flat base with a projection below that's broken and may have been used to anchor the figurine to another object. Comparison with the corpus of copper alloy male figurines and the variety of male perizomata published by Sapunas Aklaraki reveals many close parallels for the dress and hair and a few for the stance and gesture, for example, in bronze from Archanes or Traustolos. The best parallel, however, is the ivory, stone, and gold kouros from Palekastro. This evidence strongly suggests a date in the Neoplacial period, but where it was found remains a mystery. Bronze and ivory figurines from secure Cretan contexts offer a range of possibilities, including peak sanctuaries, sacred caves, as well as palaces, villas, and settlements. But we'll have more to say on this subject in a subsequent publication. As Bobby Cole noted, for now, this distinctive hairstyle marks the figure as a male in the prime of his adult life. Who he was and what he meant to Bronze Age Cretans will remain a topic for future study and debate. Thanks.
I don't know. Is there any questions? No? You can move on. It's late. Thank you very much. Thank you, the whole team. And we continue with a paper I reeditioned. Bluish-black metal objects from the Neopalatial cemetery at Poros, Crete, by Nota Dimopoulou, Alessandra Zoumlia-Meyer, Philip Betancourt, Giorgos Ethimiotakis, and Susan Ferenc.
Yes. Oh. It's a bit different from what we had on the computer. It doesn't matter. Well, Crete, we are talking about the area of Heraklion. Poros was the port of Knossos. You see the area here, indicated with this oval at the top. You can see the Venetian walls, just for orientation, the modern port and the airport where probably some of you landed. Poros was connected to Knossos, which is down here, through the way down or up the river Keratos. We are seeing the center of Poros here, and you still see the shape of the Venetian walls on this side here. And the Venetian port, of course, up here, with the border port. So closer, you can see it is a very populated area. Nota, who excavated this area, says that it was not a difficult excavation. I don't believe it. She was digging down here and this street here, even inside the yard of the school and at the threshold of some people's door. And she found, she dug out 6 tombs, which, I'm sorry, the layout is completely different. I don't know why. The tombs measure 60 to 90 square meters and are 2 meters high. This is one of the tombs. You can see this is the opening of the excavation. It's not the original entrance. The entrance is on this side. There was a dromos, which is a corridor to enter the grave, and there were dozens of people buried in these structures, all of them. This is a different tomb, again, on Icario Street, the other one. And this is Nota Dimopoulou, who was digging the 6 tombs at the time, in tomb 1986. In these tombs, as I was saying, there were buried dozens of people, and whenever a new body was brought into the tomb, the older bones were pushed to the side and put into niches, together with the offerings, the various objects of the funerary ritual. Altogether, in this area, there are 9 excavated tombs, and 6 of them have been excavated by Nota Dimopoulou. They are dated around 1750, 1450 BC, and they contained a lot of very rich jewelry. We studied only the objects from the 6 tombs excavated by Nota, and there were about 200 different objects, and you can see there are various materials here. Gold, any amounts of gold, of course, stones like carnelian, amethyst, obsidian, Faience as well, like this is faience of different colors and so on. Now, among these many finds, there were several examples of bluish black, very shiny, and iridescent beads. These materials has been described in in the past as hematite or black jasper, black marble, and even as meteorite. There is no kind of meteorites which looks like this, but yeah, there you are. We analyzed this material by XRF again, and it is a copper-based alloy containing arsenic, iron, and some sulfur, apparently. So you see here the barrel-shaped bead. It contains 0.7% of arsenic and some iron and traces of sulfur. So you can see the surface is highly polished. The patina is very solid and has a bluish tinge. An example of these beads in combination on a necklace, now a reconstructed necklace. This is the bead. And you can see there are various materials around here, like smoky quartz, obsidian, carnelian, and so on. So this black stone is our material. And you see here, it is again some copper containing some arsenic and iron and traces of sulfur. In Tom P. 1993, there were 44 discoid beads with the same composition. You can see here the copper corrosion between the beads. They are stuck together because of the corrosion. In this case, one of these beads seemed to contain low traces of gold, so I was quite excited, because this would have been perhaps a hint that this material would be similar to that of the Egyptian hemtikem, which means in Egyptian black copper. And it is an artificially patinated alloy containing small amounts of gold, about 1% of gold, small amount of silver, also 0.5 to 1% of silver, and traces of arsenic and iron. However, in this case, we had one bead with traces of gold, and the other ones didn't have any gold in them. So it must be a very different material. The material, the hemtikem material, came to Greece and Crete as the Mycenaean Kuano or Cubano, and the examples are the inlays in the triangular inlays in the daggers in the National Museum in Athens, inlaid again with gold and silver. But we have something else here in Poros. Yes, this is a different composition. The arsenic here is lower and the iron is higher, and the color is very blue, but much less iridescent. It is, however, the same type of patinated alloy. We also have this beautiful piece here, a scarab-shaped bead, and okay, it's a lentoid bead. These are from Tom P. 2000, with the same composition. This one imitates the blue iridescence and sheen of live scarab beetles. So they were, of course, sacred animals for the Egyptians. This seal comes from the Elias cemetery at Knossos, and it is made of the same material. This shows that what we call the Poros patination was not just used at Poros, it is found also elsewhere. And I would like to point out the striking iridescence of this piece here, and it is also blue. Another one, this one comes from the Epanogypsades cemetery, Knossos, and this one contains 12% of arsenic. Now, we are using XRF, which is a surface analysis, so it is one of the reasons why we have these very different compositions. However, the important detail in this case is the patina of the pieces. There are not only beads and seals, there are also pendants, as you see here. This pendant from the Ilias cemetery contains up 25% of arsenic. Now, the arsenic has the particular property to go to the surface during the cooling of the pieces. It has been used to produce, for example, silvery weapons, to give them the appearance of silver, but it was arsenical copper with very high arsenic content. We have several ones in various cemeteries in Crete. So this particular bead here was described as silver because of its silvery sheen, but it is not silver at all. What we noticed is that the patina nuance changes depending on the amount of arsenic we have and also the iron amount. So it seems apparently that the iron gives the bluish color, which is something I also noticed with Hemtichem. Iron was one of the elements which gave a bluish tinge to the patina of the Hemtichem and Kuano pieces. And I think in this case we have the same phenomenon. And arsenic gives the silvery sheen to these pieces. The analysis of various jewelry items from poros show that we have this bluish-black iridescent material which is artificially patinated and was employed in Crete in this period. And possibly it was a local imitation of this precious Egyptian alloy called Hemtichem, which later came to the Greek world. We have identified over 50 such pieces among the materials we studied for this project, so there must be more around Crete. This kind of arsenical copper alloy seems to have been patinated with sulfur and iron salts possibly. We have to do some experiments. I've done a lot of experiments with Hemtichem. Sulfur, of course, blackens the surface of metal in general, but this sulfur which we find here is similar, quite similar to that which sometimes I found on the black Hemtichem. So it might come from the solution they used, the patination solution, which was a water solution with various copper salts and sulfur as well. So I think there is also a similar technique which is known from some Roman objects, in particular objects which come from Tunisia. But those ones are dated to the 1st century BC. I don't believe that there is a connection with that. However, it can be a similar process. So our new ancient material needs to be further researched and studied, and we also need more pieces to be studied for this. So if you see anything similar with a bluish iridescence, please let us know. Thank you very much. This is our team, and this is our favorite activity outside of studies. So here you have Nota Dimopoulou, Phil Betancourt, Joseph Meyer, Yorgos Refimiotakis, myself, Susan Ferenc, and our photographer, Jeff van der Poel. I don't know if there are questions.
We now proceed with the last. Maybe we have questions. Yes. Oh, Yorgos, yeah. Το μικρόφωνο, παρακαλώ. Δεν ακούμε. Περίμενε. Έρχεται το μικρόφωνο.
You can tell me.
Έρχεται το μικρόφωνο.
Well, you know, this is a very long-standing debate about the origin of the so-called Niello technique. Most scholars say that it is invented Niello technique.
It's not Niello.
It's not Niello.
No,
but it may make a bridge towards Niello.
No, there is no
bit.
Niello there.
No Niello.
No.
For sure.
For sure.
Okay.
The specialist is speaking.
And we also have an example in Crete. The dagger which Athanasia Kanta excavated a few years ago. I studied it and we published it in a volume some years ago at Miskolc at one of our conferences. It is not Niello, forget it. Niello has been invented, discovered in the 1st century AD. AD.
The Mycenaean daggers?
Are
Because
not
we call them
Niello. Are not Niello.
It's not Niello.
No. No.
So whatever it is.
Hemtichem, this alloy, which
we thought it was.
It is a
in the
copper.
bibliography.
May I? A copper-based alloy containing tiny amounts of gold, like 1% of gold, 1% of silver, and some arsenic and iron in traces. This particular alloy is then artificially patinated in an aqueous solution containing copper salts and some sulfur. And it gets different nuances of color from bluish to purple, black, always black, depending on the quantity, the amount of the elements which are present in the alloy. So you can change the color of the, what is this? Why is this? Oh, yeah. You can change the nuance of the patination changing the amount of elements present in the alloy. But it is not Niello. It is wrong, completely wrong.
We all say Niello.
I know, but
No, it is.
But it is wrong.
Now we know it because it has been analyzed. Okay. Any other question? Yes? Το μικρόφωνο.
Is it intentionally alloyed material or just impurities?
Well, in Crete, we have most of the time arsenical copper. That's why I'm saying most probably this bluish iridescent material has been surface treated with probably some sulfur solution containing also iron salts. That's why I believe that.
I mean the silver and gold. It's just impurity.
No. There is no silver and gold in our beads.
Yeah.
It's a different material. It is also patinated, but it is not hemtichem. It is a different material. It is not what has been used in Egypt. It is not what has been used on the Mycenaean daggers. It is a completely different material.
Yes, it's understandable.
Yeah.
Thank you, Alessandra. Very interesting presentation. And I understand that here you did the XRF analysis, but because I know that you have analyzed a lot of patina, in this empty camped alloy, did you see some mineralogical analysis? Because my curiosity is...
XRF? No, sorry.
No, I say in other patina. So my question is, it's a metal, pure metal alloy, or there are also oxidation of copper and phases like cuprite, tenorite, or
of
other?
course, the patina is oxidation.
Yeah.
Always.
So my question is if there are some analysis
Yes,
that
on the
identify
patina.
the type of minerals.
Of course.
So if there are quantity of tenorite
Yes,
or other.
for empty chem, we did a lot of X-ray diffraction analysis, and it is cuprite, but it is black.
Right. So
cuprite, but
only
black,
cuprite.
not tenorite.
Thank you very much.
Okay. We must continue now. Yes, with the last
But
paper.
this is the wrong one. It's not the right one. This is the previous one.
Ah, this is, yeah.
Sorry, it's always me. Athanasia Kanta did not come today. I think she's ill.
Is this?
No.
No, this one?
This one.
Okay, yes. Okay, the title is The Foundation Deposit from Neo-Palatial Room 3 in the Religious Center at Knossos by Athanasia Kanda, who is absent, as we just learned, and again, Alessandra Zumlia-Meyer.
Athanasia, I phoned her last week, and she said that she had a flu, and she hoped to be here today, but she didn't come, so.
Another flu. Yeah.
Okay. This is her excavation. It is Neo-Palatial Room 3, and also the location of the foundation deposit. The date of this room is 1600-1500 BC. You see in the corner this rounded slab of stone, and that was the place where this deposit was. When the slab was removed, there was a vase underneath, a vessel containing charcoal. You see the shape of the vessel here. And when the vessel was removed, there were several objects underneath. You can see there a bun ingot, for example. This one is a bun ingot. You see a blade here. You see axes, one here, and yes, you can see here a gold ingot, a bronze axe, a gold axe. You will see them again. So the largest object found in this deposit is a bun ingot, which is a simple unalloyed copper with some traces of arsenic, which we always have. The most impressive object is for sure the gold double axe, which you see here. It is incised, it is decorated. A parallel is found at Archaeometry. You see it on the right there. This is from Archaeometry. It was a cave where hundreds of axes have been found, and 7 of them, if I remember right, were made of gold. But this is the one which is most similar to our foundation deposit axe here. So the axe blade is made out of a folded gold sheet. It only contains 3% of copper and some silver. Most probably there was more copper in there and more silver, probably. But the intense hammering process probably had two less noble metals corroded out of it. As you see here, part of the sheet which was folded over is partially detached. There was no solder there. The axes were only hammered. The decorative lines are incisions made with probably with a point made of copper or some flint, perhaps. The handle was a rolled up sheet made of a gold alloy with 0.5% of silver and no copper. Again, most probably the original copper and silver amount content was higher but the intense process of working had them disappear. There was also a double axe of silver, which you see here. It contains around 4% of copper and 4% of gold, more or less. 4% of gold, 4.4% of gold is a bit of a strange alloy, perhaps, but we have several silver alloys in Crete, for example, at Petras, of silver containing gold, and some of the pieces even contain 20% of gold. For example, your ring, exactly. So the silver axe is made in the same way, by folding the silver sheet. You can see here the line where the sheet was folded. Then we have this copper-based axe, which is made again with the same technique. It is also folded. It is arsenical copper. The handle contains much less arsenic, but both are heavily corroded, so most probably part of the elements have gone because of corrosion. What is interesting, yes, I wanted to show the rolled up handle again. It is the same technique. On top of the bronze axe, you can see here a small iron axe. You see it better here, I think, and it is again meteoritic iron. It contains around 7% of nickel and traces of cobalt, so we have again an example of a meteoritic iron in Crete. You see the axe here, this is the handle, and you see it better here, I think. It is very corroded, of course, but yeah, the nickel could be still seen. So the size and the proportions of the four axes can give an indication of the value which were attributed to the different metals in this period. You can see the meteoritic iron is tiny, tiny, gold and silver more or less the same, and bronze is much bigger, so cheaper, of course. Beside the four double axes, in the foundation deposit, there were also four different trapezoidal metal ingots, which you see here. One was gold with traces of silver. Another one was silver. The second one is silver, this one. And it also contains 4.5% of gold. And then we have two different copper-based alloys. One containing some tin and some arsenic, and the other one contains even some lead. What it means, you tell me. It is quite interesting to note that the axe and the ingot have roughly the same kind of composition, so that these small differences are probably due to the working process and to selective corrosion of copper. That's why the copper in the axis is slightly lower. There was also an olfactory blade, arsenical copper with 4% of arsenic, the common arsenical copper alloy which we have in Crete. And there were also several precious stones. I don't like to use the term semi-precious because it is not appropriate. And they are also cut with this same shape, trapezoidal shape. It must have meant something, but what does it mean? We don't know. The three lapis lazuli beads have rectangular sides because they were imported like this, most probably. They couldn't cut them in a trapezoidal shape. There were also a gold band and gold bosses, all coming from the Neopalatial room. And it was quite strange. We didn't know what to do about them, what to think about them. But Athanasia came up with this suggestion. She thinks that it was a wooden xonon, a statue made of wood, perhaps, which had these bosses, similar to the figurine from Maya Triada. It is a hypothesis, but yeah, it could be the explanation. To conclude, the foundation deposit from Knossos gives a glimpse into the ritual habits of the Minoans. We see all these precious materials hidden under the wall, really. It also gives a very clear idea of what was considered precious at the time. All of these materials are imported from elsewhere. The copper comes from Cyprus, we say. The silver, most probably from somewhere in the Aegean, if not further east. The amethysts and the gold, and perhaps the carnelian, possibly from Egypt or Anatolia, we don't know. The lapis lazuli comes definitely from Afghanistan, and the meteoritic iron fell from the sky. Thank you for your attention. I'm sorry that Athanasia is not here, because she would know everything about the excavation and details, but yeah.
Still, there might be any questions, comments?
Tom.
And now, yeah. Is that working? Yeah. So what you mentioned the trapezoidal shape and not knowing if it's significant, and I've always been fascinated by this deposit since Athanasia found it. There are foundation deposits mentioned in Near Eastern sources, texts, and they could be bricks rather than ingots, so that they're building blocks, so that they're meant to imitate the structure. And so if it's a foundation deposit, you're asking for some divine blessing or something. Yes. And so they're actually bricks, as though they were the building material of the building. And I think there are Near Eastern parallels that describe it that way. Yeah, yeah. So
you passed me the reference.
So it's a conscious shape.
Yes, yeah. Excellent. Yeah.
Any other questions?
Yeah.
What are the suspected sources of meteoric iron for that time?
Oh, well, meteoritic iron falls everywhere on the Earth, actually. The only reason why there is more now in the desert or in Alaska or whatever is just because they didn't use it there. But I don't think it was imported. I mean, I know about people now who are studying meteorites and just put boxes out in wherever and collect whatever comes down. I'm serious, really. Serious university studies, several universities together, and they all, every single member of this team, they put out boxes to collect meteorites, tiny ones. Apparently, every day they collect small pieces of meteorites in these boxes. So, I don't know. I'm not an expert.
Many of them falling.
Yeah.
So my question was actually, recently there was a Bronze Age dagger from Switzerland that was suspected, maybe originated from the Estonian Kali meteorite, which impacted in 1500 BC, so in the Bronze Age.
Yeah.
And lately we have had pieces as large as 5 kilograms by the metal detectorists from there. So anyway, I was interested if you have any possible sources, but it seems that it hasn't been investigated.
But I don't know anything about sources of meteoritic iron. I thought Gilberto, what do you say? The meteorites fall down anywhere.
Την κυρία με το turquoise.
Yeah.
You want to say the same thing? They do fall everywhere, but it's not easy to collect a small piece of meteorite and make them into a bigger object and then work it. So usually the meteoric iron objects that have a certain size, they come from a large meteorite. So they are often documented and known. That's why sometimes it's possible to attribute the meteorite. So again, because you cannot just collect a small stone of this type of material, melt it together and then make a big object, because it's not something that at the time was possible really. So you need a much bigger piece. So it's usually something known.
Yes,
it's usually something known and documented. I mean, often, not all.
That's what I also wanted to say about the Inuit harpoon I was showing before. They managed to detach a few pieces from a big one, but I believe meteorites made of iron meteorites, have been used for making iron afterwards.
Yeah, but the meteorites are, you don't actually collect them easily. Like micrometeorites, it's another thing. They are in sediments and other things. Big blocks, either you see them falling.
Yeah.
Because 90% of the stuff that is brought to us as meteorites is wrong. His legs and other stuff. So whatever you find that's around is usually not a meteorite.
It happened to me as well,
So
yes.
usually what happens is that you see them falling, and then therefore they know that it came from the sky, they don't stumble on them.
Which is made of iron.
Therefore, that's why they are so valuable. And we find them either in Antarctica because it's black and white, or in the desert because it's black and white.
Because it's visible.
Otherwise, you don't see them.
Yeah, that's what I mean. But they fall everywhere. So, who knows? Maybe they saw it falling.
Yeah, no, exactly. So that's probably documented somehow that a big meteorite fell somewhere. It's very possible that they can document this.
But we don't know.
Other question? No? No. Huh? So we finished.
Yes.
For today.
For today.
Bravo, Mas.
So we continue tomorrow and we begin at 9. And the members of the commission, please, the members of the commission are meeting now after this session at the hotel.